Hello everyone, welcome to another stream. How's it going? Welcome there, Doro. How are you, my friend? Right. Get some headphones. Hey Zero, hey Glorissa, hey guys. Ooh yeah. So, thank you. Yeah, it's Father's Day today, so I got to look extra nice. Went around the parents and church and everything, so yeah. But I did a little bit of work on the project off stream, but not really on the project, right? On those diagrams. I don't want it to be... I don't want to spend another stream after this one on PBR recapping. So I got some new lovely diagrams. And so they've got like titles now, and they're more correct as well. So I did a full pass on it. So we've got this microfacets one. We've got this diffuse one, where it changes if the metal goes up. Yeah. And you got this specular one, where it changes with roughness and metalness. Yeah, that one. BRDF one. Normal distribution function. Geometry shadowing. Boom. Fresnel. You can tweak some bells and whistles as well. And oh, this one hasn't got a title. Oh, what happened to that one? Oh no, it's because there's no roughness. Boom. Yeah, so today we're actually going to be doing the recording, going over these little diagrams and things. Yeah, and putting that into a nice video for folks who want to learn about PBR and put it in their engine. Should be cool. So, and yes, Glorissa, I have seen your message, by the way. I've just did a little short reply. But yeah, I probably will want to reply to more of it in a bit more detail later. It's been a bit busy. But yeah, it's a good find though. I've not tested out that virtual memory page allocation stuff yet. Something I want to do later though. It's good. But yeah, it's a very complicated set of things. Understanding how the OS implements virtual memory, because the documentations say things and you have to sort of test them out for yourself as well. Yeah, it's very strange. But yeah, is that your primary platform you develop on, Glorissa? Is it Windows do you use? Because I noticed you yeah, I think you use Windows primarily, or do you use both? So how do I want to start this little devlog off? I think what I would like to do is mention, oh yeah, demonstration of PBR. What we have, correct. So I think I might want to turn the chat off on this one because I've got little diagrams and things. So I'll turn it on. Yeah, I've got little keys and stuff, and the chat will just get in the way, unfortunately. So it'll be turned on the next ones. I do use Windows primarily, but I have Linux, so that can be an option. Cool. That's nice. Right, so there you go, I guess that out of the way. I'm getting my first Linux distro today. Oh, exiting Mint. Will be okay. Your first one is to be Mint, fair play. Yeah, I think one of my first was Mint back ages ago now. Yeah, it's like a nicer looking Ubuntu. Yeah, Ubuntu's always a bit weird, but yeah. Nice. Just be careful when you install it. Make sure you you're best to probably put it on a different hard drive if you can, or different storage media, SSD or whatever it is, right? Because it's very easy to accidentally overwrite your existing, um, yeah, your existing operating system. So just be careful about that. That's what I, especially if you're installing Windows after Linux. Windows would just be like, other operating systems, and it just wouldn't do anything about it, and it would just, yeah. You got to be careful installing Windows after. So I just do the two storage. I have one for each operating system, and it's quite nice. Create a 400 gigabyte partition. Fair play. Yeah, you can do that. Yeah, yeah, you can do it. It's just like if it's your first time, you can quite easily mess it up. Even if it's not your first time, you can also mess it up. So having measures in place to stop it from actually happening completely is always a good idea. Yeah, 3 times to be sure. That's cool. Yeah, if you want it to be in that configuration where you have the two partitions, there's no way around it, obviously. You have to just be super careful. Yep. Right, so I guess I just want to do a couple of takes on this one, eh? Wait a minute. How's the camera looking? How's my hand looking? Yeah, that'll do. It's been a while since I've done a devlog now. I'm not doing this again. Now, the music's on another channel. So on OBS, you can set up so that the desktop audio is on a different one of these tracks, as they call them. So you say desktop audio is not on track 2. Track 2 is the recording track. So Twitch, this is the streaming track, and then on this track, that's the VOD channel, or the VOD stuff. So the microphone only goes through to the VOD. So that's how I get around all the copyright stuff, basically. So that's quite nice. But yeah, I'm gonna be doing like I'm not gonna be doing like another devlog where it'll be like this, where it's all planned out. Unless I do something which I'm completely unsure about again, which will probably not happen for a while. Zoom. Hello everyone, welcome to another devlog. So over the past couple of weeks we've been working on implementing PBR. As you can tell, the spheres are looking much nicer. We haven't got as many spheres in this scene here. But you know what? Okay, I'm just going to do a practice run. I've already messed it up. But yeah, so we've got this scene with PBR, and up here we've got a bunch of options, or a bunch of sliders and settings we can use to debug our PBR code in shaders. You know what? Yeah, okay. I'll do that one more time. Hello everyone, welcome to another devlog. So over the past couple of weeks we've been working on putting PBR into the game because I didn't really have a good way of shading these spheres that we use to render our scenes. And I want to have something which will make the scene look good, and also but yeah, I'm not sure if we're going to go for realism, but typically when you see games these days is they basically have they have realistic lighting like PBR, but they don't necessarily have a realistic like materials, if you will. They kind of make things look either like cartoony or okay. Better rambling. I think I can do that. That's better. Hello everyone, welcome to another devlog. So today we're going to go over this little PBR implementation that I've been working on over the past couple of weeks. So I wanted to make the spheres that we're rendering just look better. And PBR is something, so it stands for physically based rendering, if you didn't know what PBR stands for. And it basically, per pixel, you're doing kind of physically inspired calculations, like based on like where the lights are and how the sort of rough the surface is and if it's metal or plastic, basically. And it really improves the quality of how the rendering looks overall. So we're not really going to go for a realistic art style in this game, but something that you see in most games these days, if they don't go with a realistic art style, is they still have PBR just to make things physically look like plausible with like the lighting and that, but they will customize, they'll do some more post shading stuff to sort of make things look more like arty or something that's not realistic, right? So we'll probably do something like that afterwards, but I just wanted to make the overall primitives that we're rendering just look much better. So up here we've got a bunch of these little dials that we've been using to have a play around with the materials, and also the lighting and stuff. You can change the colors of these lights as well, and also their intensities. And also there's different little viewing options, which we'll go over more, where we can just view certain aspects of the PBR shader code and have a bit of a play around with the settings and see how it responds, just to make sure they are all correct. So yeah, let's get into PBR and how it works in the engine. Cool. I think that's good. That was a good take. So you know, it'd be a bit of fun. Let's re-enable all those spheres. Remember before PBR, we had like tons and tons of spheres. Let's go in the screenshots folder. Should we try and get this scene back up and running with PBR and just see what it looks like? That'd be interesting, wouldn't it? Prepare. So we're going to the prepares. What is this? Insert. All right, I think that's it. Now, hopefully this still works. Yeah, maybe. It's the hardware holds. There's more calculations, that is right. Oh boy. What is this? It's very glistening. Oh my days. Bzzz. But yeah, that's when they're super reflective. Holy, what? Yeah, maybe. Maybe we shouldn't be going for ultra small spheres with PBR like this. Well, yeah, you probably want to have some form of different. Yeah, this is pure metal. That's very interesting though. There's your plasticky looking ones. I don't really have the LED sliders anymore. The frame rate is not as good as it was though. Oh, is it? Is it really? There's a compression artifacts. Right, well, that's interesting to see at least. So yeah, we should probably be careful if we're doing. We should probably be careful with doing very small spheres. That is okay. But maybe maybe we can have some texturing, which allows us to get the material properties from textures. So it could be more. It could be, yeah, maybe like albedo as well. Yeah, it's all stuff to have a play around with. Let's go back to the simple way. That was interesting. Right, so what do I want to do? Um, um, so hmm. Oh yeah, the resources that I learned from. That's what I want to start off on. Because I'm not going to provide a decent perspective from the maths sort of. Well, from the maths perspective, I might say. I would like to link to. There, it's a good screenshot. Bit blinding, but the way it is. And then there was the other one that I used as well. Oh. Physically based rendering. It was that one. So that was the other resource. And then we'll dump this one in as well. Oh, and learn OpenGL. Alright. Right, so we'll obviously drop these links somewhere. Where's a notepad? Okay, right, Kate. New. So this one is the physics and math of shading. Compute. Oh, PBR. Yeah, it's kind of a tutorial. Gives, I don't know, it is definitely, you don't get an implementation after watching that. It's close though. It's kind of like, it's a good starting point. This one is a blog post because some people like to read. And then PBR. PBR/IBL. Learn OpenGL. Yes, they're my references. So I don't know, I might drop them into Twitch. So yeah, that's what we use to figure out PBR. And that's what I'm going to go over. Oh yeah, there's this one as well for the cube map. Yeah, it's not HDR though. The difficult part is getting some lighting source working properly. Yeah, I only have directional lights right now. Yeah, there's other more the problem is I don't have a scene. So I want to probably build up a nice test scene first, which is going to resemble sort of what the game will be like, and then come back to doing like proper lighting, basically. Yeah. Hey, Egotist, welcome, sir. How you doing? Yeah, I'm doing good, my friend. Doing good. Just been to church and then around my family's, my parents. and saw my grandparents and ate food. It's Father's Day today. It is used in lighting for reflections, but not used for used for reflections, but not used to provide any bright lights. It's in the sRGB color space, so it doesn't go outside of 0 to 1. So you don't get any brightness. Awesome. Good to hear, good test. Good to hear. Yeah, references. Probably want to have the game running as well, so I can go after that on to talk about the cube map, isn't it? Yeah. Okay, so before we get into any of the implementation, sorry, I've had a burp come in, so just get rid of that. So before we go into any of the implementation and any diagrams that I've made, I want to reference all the things I learned. So before we get into any of the implementation or the diagrams that I've drawn, I want to show all the places where I learned PBR from. So there's this really great video which goes over the sort of physics and maths of shading. So I won't be covering it in this detail. I want to provide more of this surface look and from a programmer's perspective. But I've watched this video like over 10 times and it's really great. I learn new things every time I watch it. Highly recommend watching this one. All the links will be down in the description. And there's this computer graphics tutorial by Victor Godin. This is what I used to sort of get the code up and running, and then I heavily refactored it afterwards. And what sort of are the different formulas that I use today. So he's done the research there. There's also this blog post here, which is about image-based lighting, basically PBR as well. So if you're into reading, there's this blog post here. And also there's a Learn OpenGL one as well, which I definitely looked into the image-based lighting section here, which is the cube map and things, and getting color from the cube maps. So speaking of cube maps, there's this other one here. This is where I got the cube maps from. The issue with these is they're not HDR. So when you do your you can't actually get proper lighting from this. You can have a value from 0 to 1. So you're just going to get color information, not necessarily any intensities. So, but it's still a good place just to start off with. So I've used this night one here and this daytime one here, but there's plenty more you can take a look at. So we just see that in the game right now. So you see here that these bright lights, they're not contributing to these, like this, as much as the sort of fake lights that we've got, which you can't really see in the sky because they're just saying, hey, there's light coming from a direction, and with PBR they sort of look like they exist up there. But yeah, right, so let's get into the details. Is that I wanted to go over the PBR thing with the cube map thing? I think it was, wasn't it? Yeah, that'd be good. All right, so thank you, Zaka Zaka. Oh yeah, Zaka Zaka. Was you one of the people who wanted to see how it looks like with the old scene? It's pretty crazy. I just looked at it, so I'll give it a show because I'm sure people have entered. So this is the old scene where we had like just crazy amount of spheres with the LOD thing. The frame rate is tanked, and this is plasticky looking ones. See, they're really small. So that's when they're really rough. That's when they're really reflective. This is when they're metal. The metal ones are really glistening. with that sort of blue light that travels over. But yeah, and you can really see. I think we've got a bit of a glitch actually with the anti-aliasing. Yeah, the anti-aliasing is not on anymore actually, so that probably contributes to something. But yeah, this is kind of crazy. So yeah, we should probably be careful of very small spheres moving on. But also maybe we could probably have different. We could probably play around with it some more when we have more of a scene that resembles the game, and that maybe we got to get some. Yeah, maybe we'll play around with the implementation a bit, I guess. It is, isn't it? So we probably want to make them. The art style is going to need bigger spheres, and then also probably tweak how the PBR works. But that's cool. It's stuff to play about with. Right, we're going to be redoing the renderer anyway. We're not going with the small spheres. They're on grids. But we'll get to that when we move on to it very soon. Those details will come. Yeah, so I want to get into like microfacets, basically what they are. Yeah, so I think let's start off with that. So I want to show some diagrams first, and then we'll get into the code. So what to remember, there is these. We've got to take a break. So after diffuse, and we'll do specular. Yeah. I think we'll show. We won't just be looking at diagrams. We're also going to be looking at the spheres as well. Oh my days! Get rid of that. There we go. Back to sanity. So right. So microfacets. Okay, so now we're going to show some diagrams that I've made inside the game to demo what PBR is, and just, there's a title here, and there's also a key to the right hand side, but with some colors based on what is in the diagram. So what we have is the light source here, which we call the sun, and we have these light rays which shoot out. Now, when they hit a surface and it's perfectly flat, they will perfectly just reflect off with the standard reflection formula. But in real life, even if a surface appears flat, it is not necessarily perfectly flat at a micro level. So this is what microfacets are. They are sort of this, basically saying that surfaces aren't perfectly flat. So the rougher it gets, notice how these reflected rays, the direction changes. So in PBR, for games at least, we do not model these bumpy surfaces explicitly. They're all done statistically with just a bit of maths, so it's cheaper to calculate. So yeah, microfacets. Yeah, that'll do. Is there anything else I want to mention or do a retake in? Maybe I could do it again, just so I got another take. Hey, Piggy Bank. No, I'm just in a devlog. Hey, Taylor, rather. Good to see you. Yes, I'm just in a devlog, which is basically giving more of like a programmer's perspective to PBR. So I'm not really going to go into sort of the maths as much, because there's other resources which do it way better. I just want to make sure that there's another resource out there which is more programmer focused, if you will. So just to give another sort of perspective from it, and then people can go and look at other resources too. I know, right? Maths. yeah, so I'll be going over, I've got these diagrams and I'll just be chopping up into a nice video. And hopefully at least one person, um, you know, likes it. Stream froze. Oh, shoot. Thank you for that. The camera must have got disconnected and reconnected again. That's sad. Was that during the take? I didn't have a take anyway. But yeah, so just doing a devlog, and then I'll get back to the other easier devlogs. So this one I prepared like all these lovely diagrams, which took way too much work. But yeah, so I'm not doing this again for a while. After take fair play, thank you. I don't have a take just in case. Another one. Right, so okay, I realized already. Okay, so in these diagrams, we have a title here, and we also have this thing on the right hand side, so like a key. So you'll be able to tell sort of what these things are, just in case you missed me saying it. So we have the sun here, and it's shooting rays onto this surface here. And notice how they just perfectly reflect off using the standard reflection formula. They just perfectly reflect off the surface into the sky again. But obviously, nothing is perfectly flat. It actually has a little bit of bumpiness to it. So in the real world, if something's completely flat, at a micro level, there is something that it, you know what, the first take was actually way better. I'll do another one just in case. Okay, so we're going to be talking about microfacets now. What are microfacets? But just before we get into that, there's a title here for you guys to keep track of where things are. And there's also always a key to the right-hand side, so you can see what we are pointing at on the, you know, let's just go with the first one. Note to self, first one's fine. I need to not do retakes. Yeah, so then we'll talk about diffuse next. So, yeah, I think I could do one more take actually. I've got an idea. Right, so we're going to talk about microfacets now, but I quickly just want to talk about these diagrams. So we have a title here to keep track of where we are, and on the right hand side there's a key, and this key you can obviously use to figure out what is on this diagram here. So microfacets are basically saying that, you know, you've got this flat surface in real life, and at a micro level, it actually is not perfectly flat, depending on how rough the material actually is. So here you're seeing a perfectly flat surface. The light source is here, and it's shooting its rays out here. So when they hit the surface, they're perfectly reflecting. So if you increase the roughness here, you'll notice that the rays actually bounce off at a different angle. So again, this is at a micro level, and in computer graphics and for games especially, I guess, we do not model this microfacet explicitly. What we actually do is have some statistical maths, which will basically say, will give us, you know, how much, what's the intensity of the light and how many sort of things are shadowing and other things which we'll get into in a bit. But yeah, we don't model these explicitly because if not, it'd be too computationally heavy. It's just done with statistics. So again, a key parameter here, which we just picked up on, is there's a roughness parameter for every material. And you see the things in the background, they're changing based on the roughness. We'll just take a quick look at those now. Right, so I think that was better. I got 2 takes now. Right, so here we have a close-up of the spheres. We're just going to modify the roughness here, and notice how it just kind of just averages out the rougher it gets, because all the light rays basically just, you're not getting perfect reflections anymore. You're getting light coming from all kind of other directions, so it kind of grays out, if you will. And then we have metalness here, which is another PBR parameter. Basically, this is dielectric, so everything that's not metal, and over to the right is metal. It's physically not correct to have something in between, but the maths supports it, so you can do that if you want to. And you can see there's more reflections here, which you'll understand in just a bit. And as we get more rougher, it kind of just grays out. So obviously there is a surface color, which you can change as well. So that just changes the surface color. It was kind of a gray before. But yeah, as it gets rougher, it kind of just, it gets more and more to that color. Right. Now I'll do that one more time. One more take. One more take. The first one's often best because you have a similar mindset as the listener. Second, beyond that, you just repeat yourself. Yep, and then repeating the mistakes. You know, or you've already said the thing, so your brain's like, I'm progressing on from this, and just dumps it out the brain. Okay, so we've got the close-up here of the spheres. So we're just going to go over the main parameters of PBR. So the first one is roughness. So as you saw, it creates that rougher surface. So rays aren't really going to perfectly reflect anymore. They're going to sort of come from all over when you're trying to shade a particular pixel, right? And then the other one is metalness. So on the left, it's dielectric. On the right, it's metal. So on the left, basically non-metals. So the in-between is technically or physically not correct, but the math supports it, so you can do it if you want to. So see the roughness increase here for the metals, and as you see that perfect reflection, which we'll get into why there's more of a perfect reflection soon, kind of starts fading out and it gets more blurry and blurry until it's kind of just grayed out. So it's grey because obviously the surface color was grey, but you can obviously change these around and change the surface color too. Right, so let's get into the next diagram. Yes, very much so. Very much so. I'm getting much better at it though. I used to be terrible. Yeah. So if you have anxiety or anything like that, you can get over it. It just takes time. Why does Mel behave like that? What do you mean like that? Define that. Oh, reflect light. Because it's specular. Yeah, we are going to get into that. Basically, there's diffuse light, specular light, which you'll see in more detail. But metals, the color comes from specular. It does not come from diffuse. Metal takes no diffuse light. Diffuse is bouncing inside the material and back out. Yeah, so there's no, whereas a non-metal will have diffuse light, which contributes to the color, and they'll have specular light, which contributes to the brightness, something like that. It's kind of like a gray color. Yeah. So that's the basic idea. No, metal does not absorb any diffuse light at all. Sorry. Yeah, the metal absorbs it all. Completely absorbs the diffuse, the light. Yeah. So when so the light that doesn't the light that refracts into the material just gets completely absorbed. The light that hits the material and reflects, that obviously that's the one that contributes to the color. Yeah, that's the way of saying it. From what I understand. Yeah, it's very. Yeah, I would not. something where I was like, huh. Like, and then you sort of, but yeah, it's interesting. It didn't feel um or like an it didn't come instinctively to me that that's the way it behaved. Right, so something to understand about materials and lighting in general is there's this thing called diffuse lighting. So what diffuse lighting is so you have your sun here and you have your light rays, and here's our surface. I've made it so that we can sort of see inside the surface here, but imagine it's like completely covers the ground. And here's our pixel that we're trying to shade, surface normal, pointing up. Um, and when the light hits the surface, it actually refracts into the material, bounces around, hits some particles in the material, and it can reflect back out and go into the camera up here. So when it's bouncing around here, it's actually gradually absorbing the color of the material and sort of tinting the light into that color. And then, so by the time it bounces around a few times, it's really absorbed the color and it goes out into the camera. So a thing to take note is this is true for dielectrics, so non-metals. But for metals, they actually don't contribute any diffused light. So when the light hits the surface and refracts into the material, metals completely absorb the light, and then no light comes back out from the metal. I probably need to do that one again. One more time. Is there a roughness slider on this one? No, there ain't. Right, so when it comes to PBR and lighting in general, there's something known as diffuse lighting. And so we have our sun here, and the light rays are shooting towards this surface. So we have a surface here. I've made it sort of see-through so we can see what's going inside the surface. So it's this sort of teal color. And here's our pixel that we're trying to shade, and there's the up vector. So when the light hits the surface here, it will sort of refract into the surface, and as it's bouncing around little particles inside the surface, it's absorbing the color, and then it will eventually bounce back into the camera that we're rendering from. So basically this is, my brain completely just froze for a minute. What was I even going to say? So it bounces around into the camera, and then I think the next one was just literally talking about metals. Right, one more time. Right, so with PBR and lighting in general, there's a thing known as diffuse lighting. So here's our sort of light source here, and here's the light rays, and they're going to hit this surface. You notice this surface is kind of see-through, if you will. And when the light hits the surface, it will bounce around these particles and sort of absorb color from that material. And then the light will eventually bounce back out into the camera. So this is known as sort of the diffuse lighting. So this only happens for non-metals or dielectrics. Metals do not sort of have any light that refracts around and reflects back into the camera, because the metals fully absorb light that refracts into the material itself. But they still have other ways of getting light from the surface, which we're going to next. But I think that one was better, but I got two to pick from. Oh. Right, so roughness. Wait, will roughness affect? Based on the Fresnel, it will affect. Yeah, I won't talk about that. Right, do I want to get? Right, so the other kind of lighting to be aware of is specular lighting. So this is when the light hits the surface and reflects off of the surface as opposed to refracting, right? So it reflects off and it will then bounce, it'll reflect into maybe the camera or maybe miss the camera. So as we increase the roughness, obviously these reflected rays will change because the microfacet could be more bumpy and it won't necessarily be a perfect reflect anymore. So one thing to keep note here is for dielectrics, so non-metals, these guys have a gray color when they reflect off the surface, whereas the metals, you would actually absorb the color, like the color of the metal comes through from the reflected light, aka the specular lighting. Yeah. Yeah. I think that's all I wanted to say about that one. I'm gonna do one more take. Right, so the other type of lighting to be aware of is the specular lighting. So this is where the light comes from the light source, hits the surface and just reflects off. So it doesn't go into the material and come back out, it just reflects straight off the surface. So this is affected by the roughness as well. So obviously the microfacet will change. So it'll be a little bit more bumpy, so they won't always get the perfect reflection. So they can end up missing the camera as well if it's too bumpy. So with the metalness parameter here, what you'll notice is that when it's a sort of non-metal or dielectric, the reflected color would be gray. But when you have a metal surface, the reflected light will be the color of the surface. So it's just, this is something to keep note of. The color comes from the specular lighting for metals, whereas the color comes from diffuse lighting for dielectrics. So we're just going to see the spheres up close now and see the debug modes we have for those. Debug modes. Right, so we have this nice little viewing drop down, so we can just debug certain aspects of the PBR code. So we take a look at the lighting here. Here's the diffuse. Oh shoot, that's not a good one, is it? Oh, it is because it's metal. Whoops. Right, so here in this sort of view modes, we have a nice sort of debug view of all the different things that contribute to the color and the lighting in the PBR code. So it's very helpful to see if each aspect of the PBR code works well or works as intended. So there's two parts of diffuse here. There's ambient, which comes from the whole scene. So notice here for non-metals it shows up, whereas for metals it doesn't show up because again diffuse doesn't contribute to the color at all. The metals. And then we'll go over to lighting. Diffuse. This comes from the light sources, the direct light sources. And as we increase the metals, this is where no color no color comes from diffuse lighting for metals, right? Whereas dielectrics, you get the color from there. So now let's move over to the specular. So there's two, there's the reflected, and then there is also, it's more sort of grayed out here for the non-metals, and then for metals it's more reflective, right? Because only the color that's coming from it is the specular. And then the lighting specular here. So non-metals and then metals. Wait a minute. So this will be grayish. Yeah, the light color. Ah, shoot, you're not going to see the surface. Why am I seeing the albedo in here? I got to explain that. Hey, Cranston, they do not tint the incoming light, so reflected light is the same color. The electrons do not tint the incoming light, so the reflected light is the same color as the incoming light, which is gray only for gray lights. This is a nit, obviously, but you could imagine a material that distributes non-uniform incoming light, specular colored, from a uniform spectra gray. But that is not what is modeled here. Don't should not tint the incoming light. The reflected light is the same color as the incoming light. Right. Yes, it's the same color as the incoming light, whereas metals will tint it. Is that what you're saying? Right. Dielectrics reflect the incoming color. You're right, okay. Does not reflect gray always. That's a good idea, okay. Right. Okay, I need to do that again. That's good. Thank you so much for the correction there, Cranston. Appreciate it. Yeah, I see it here now. This is why I start questioning now, isn't it? I was like, so why? Yeah, so right. But also, why am I seeing? Oh yeah, because you need the reflection. Yeah, because the reflection. Yeah, got it. That's light sources only. Okay, this is good. Thank you there, Cranston. Appreciate it. All right. So the next type of lighting to be aware of is the specular lighting. So when the rays come from the light source, they will hit the surface and reflect. And obviously they can, they can hit or miss this camera up here. So the rougher it gets, the more the microfacet is bumpy, and therefore the rays will be less likely to be a perfect reflection. So for non-metals or dielectrics, the color of the reflection just comes directly from the light source. Whereas if you have a metal surface, what will happen is the light, when it hits the surface, will be tinted by the color of the surface itself. So here, as you can tell, it's absorbed the color of the surface and been made blue for metal, whereas for dielectric it stayed the color of let's just say gray, but it takes the color of the light, dielectric. So let's take a look into the actual spheres we see behind on our debug modes to see it in action. Right, that was better. Yeah, that was good. Thank you, Cranston. So, okay, so we've got these debug modes here, which allows us to see certain aspects of the PBR code and debug if it's correct or not. So we're going to be taking a look at the diffuse and the specular. So ambient is a type of diffuse. It comes from the cube map all around, which we'll talk about more later, the image-based lighting. So this contributes to the dark places which the light is not reaching, as well as the places where the light is reaching. So for non-metals dielectrics, you'll get color from this, whereas for metals, you will not get color from this. So just be completely black. So the next one to look at is the reflected debug mode. So this is the perfect reflection into the cube map. This is some more image-based lighting. So for dielectrics, it looks like this, whereas as we increase to metal, it'll be more visible, the reflection, basically. So let's go into the lights. Just the lighting or the color which comes from the lights themselves. Here's the diffuse. So this is for non-metals or dielectrics. And then as we go into being metal, it is again completely black. So this is the specular contribution next. Yep. So here you see more of the reflections of the actual lights themselves. And notice here we change the albedo to something that's more red. You're not seeing the red come through here for this little specular highlight because it's dielectric, but when we make it metal, that red will already come through because it tints the color of the reflected light. So if we go back to that reflected, actually see here how it's absorbed, like the reflection is that red color for metal. If we turn the metal down, it actually goes it's very gray. It's more of a gray color than an actual tinted to the color of the actual surface. Cool. That was much better. Last bit could have been a bit confusing. I guess I could try one more take. Try one more take. Right, so here we're debug viewing these spheres. We've got a bit of a reddish color for the albedo of the sphere here. So what's nice about these viewing modes is we can see if the PBR code behaves, or the certain aspects of that contribute to the lighting in the PBR code behave as they should. So here's the ambient lighting. This comes from the cube map, and you'll notice that when we increase the do you know why that this cyan light is seemingly not tinted for metal? Yeah, because the cyan light will have like 0 red, wouldn't it? Better than tinted. Let's think about that. Wait, what the hell's going on? What have I changed? Changed that one, didn't I? But yeah, reflecting red is really blue and green. Reflecting red is really not reflecting blue. Right. So why is the cyan light not absorbing the red, you're saying? So these change it. Because it had a bit of blue, I guess, and a bit of green already. Oh. It's probably got no red though, isn't it? Is that right? Color of the light is here, yeah. It hasn't got any red, that's why. So if it had a bit of red, then it would be affected as multiplying by 0. Yeah. So you shouldn't probably use a 0. You should probably have slightly non-zero for the light colors. What do you reckon? I have just a faint amount of light. Because otherwise it just times it by 0. Maybe we need that? Uh... There's a color and intensity. I guess, do you sort of like... maybe have put the maximum between something like that, maybe, and then it will at least specular. So we change the albedo now. Wait for the metals, isn't it? No, it's not changing. Maybe it's not enough still. Hmm. Yeah, I wonder. Yeah, I wonder if this is what we want. Do you reckon this is a good idea, Cranston, to have like a little bit of color on the light on all channels? Just a little bit. But then you won't get the perfect. So it could be influenced by the surface color a bit. Hmm. Yeah. It's seemingly not tinted for metals. It's because it's multiplying, I think. Lighting. Yeah, it's multiplied with the BRDF. So yeah, it's just tinting it. Yeah, I don't know if it's the best idea to do it though. Maybe that's just the artistic choice. Just got to make sure that you have a little bit of... Because if you change that... Yeah, I don't know if there's an easy way to do it, to be fair. Yeah, I think we'll remove that limit. Right. Let's do one more take on that. One more take. Right, so for PBR, we have this nice sort of viewing modes where we can view individual aspects that contribute to the full PBR shading. So if we start on ambient, this is what comes from the cube map basically. So you need image-based lighting to get this look. So this contributes to every part of the sphere even the parts which are not directly lit by the lights. So notice for dielectrics or non-metals, you're going to get this sort of color from the environment. Whereas when you have something that's metal, you're not going to get any diffuse lighting. So ambient is a form of diffuse lighting. Whereas if we go over to the reflected view mode here, this is specular lighting. And we're just going to make the albedo a bit red. And you'll notice here, for non-metals or dielectrics, this did not change at all. But as we make it metal, you see the red has already came out in the color. So now we're going to go to the direct lighting diffuse. So for non-metals or dielectrics, you're going to get the color from this diffuse. Sorry, the color of the surface from the diffuse lighting. And if we make it metal, you'll see how the color just goes. So there's no diffuse lighting for metals. Whereas you look at the specular contribution, you'll see here that the color of oh my days. I need to do a clip of that. A bit perplexed. Did I tweak something that I shouldn't have? Why is this blue? What did I do? I changed this slider instead of the metalness one, didn't I? Damn it. No. Okay. Well, I'll clip this in as well. It's fine. Right, so we go to the specular lighting now from the direct light. For non-metals or dielectrics, it's going to reflect the color of the light, and it's not going to get tinted by the surface at all, which is a little bit red. And when we make it metal, you'll see how the reflected light gets colored by the surface. Okay. I would encourage having the mental model that materials can only absorb. So that material can only absorb. So a material can only subtract red, green, blue. Never add red, green, blue. Right. Yeah, because it's multiplying it, isn't it? Yes. That is very true. Yeah, because you would get the energy would be would get absorbed into the material, and only some of it would get reflected out. Yeah, so it's red. It's got a little bit of blue and green, the material. Yeah, no, it's because it's got a little bit of blue and green already, I think, and the intensity is probably already quite high. Yeah, it's got quite high intensity as well. Yeah, guess so. Maybe that's it. Awesome. Good to know. I think we should do another take then. I think that's okay. Hmm. Yeah, maybe we could do another take. Um, you sure? Fair play. Yeah, I guess it doesn't have to be perfect. I've got other resources I'm linking to. But it just gets the general idea down. Oh. Right. Shall we... Right, so we've got the BR... Yeah. Okay. Right, so the next thing to be aware of when you do PBR or any lighting in general is, you've seen that the rays have been coming from the light source and happen to go into the camera. But when we actually do shading on the GPU, we cast a ray from the camera into the surface that we hit. And this is the pixel here that we're coloring. It's not kind of exactly how it would look, but imagine this is the sort of area the pixel is touching. And obviously, if you see that the microfacet is, is as bump is wait. Right, so something to be aware of when you do PBR or lighting in general in a shader is what you've been seeing at the moment is that the light comes from the actual light source and hits the surface, and maybe it goes into the camera, maybe it doesn't. But to make things a little bit easier, we actually do the lighting from the other way around. So we'll cast a ray from the camera, and we'll calculate how the light behaves on this in this area that the pixel is touching, and how much of the light has reflected into the camera, how much of it is missed statistically, and how intense it is, and all those sort of things, which we'll get into just a bit. But you'll see how essentially this microfacet is probably like way smaller than this for the pixel, so you can't really have every ray. You can't really count every single ray that perfectly reflects. It has to be done statistically for it to be fast. I think we can do a better take than that. Yeah, one more time. Right, so something to be aware of is that we have been doing the lighting, imagining it from a light source where the light source shoots out the rays, hits the surface, and just happens to go into the camera at a certain pixel. But to make things a bit easier, the way renderers work is they will, for every pixel on the screen, they shoot rays, or they have a ray to the surface that they've just rasterized, depending on how the renderer works. And this, this is a rough idea of the pixel on a surface, but it's not to scale, or the shape is not exactly correct. But it's just an idea. But the ray will come from the camera and it'll be at the surface, and we do our lighting calculations based on sort of this ray from the camera. So it just makes things a little bit easier, and you're still able to produce a physically kind of what do I want to say around this then? You're still able to produce physically. Yeah, I might do another take on that one. Right, something to be aware about when you're doing PBR is that we don't actually trace every single ray from the light source. And you've seen in the current or the previous diagrams, is they've come from the light source and they just happen to go into the camera. I guess you could probably do it this way, but it's just a bit easier if you trace the rays from the actual camera themselves. So the renderer could be just a rasterizer, and you just take a ray from the rasterized pixel from the camera. And this green box here is meant to be the sort of area of the pixel that we are kind of shading. But it's not to scale or anything. So you'll use essentially the vectors. You'll use a bunch of different vectors and calculate a type of, you would statistically work out all those light rays that could possibly hit this area and how many of them are going to go back into the camera itself. So we'll just dig into that more specifically now. It's admirable that you're working through a prolapsed anus. Is that true? Wait, you're talking about this thing here? I have no idea. Cool. Right, so one of the things in PBR is this thing called a BRDF. So, all right. One of the key aspects of the PBR maths code is this thing called a BRDF. That stands for a bidirectional reflectance distribution function. So it may sound a bit scary, or you might get a bit lost when you hear it. But if you just break it down, it's actually kind of simple. So it's bidirectional because there's two key vectors that you need to inputs into these sets of formulas that come together. So one of them is the direction to the light source. So from the surface, or the center of the surface that we're trying to light, there's a direction towards the light source that we're trying to light this pixel from, and there's a direction towards the pixel that we're trying to render on the camera. And then we also have some other vectors as well, which is the surface normal, and this thing called the half direction. So you calculate the half direction by adding the light direction and the view direction together and then normalizing again. This gets you the halfway point, and this is used in a few of the different formulas inside the PBR formula itself. So let's take a look into those now. Maybe I should do that one more time. So one of the key pieces of maths inside this PBR code is something known as the BRDF. So it stands for the bidirectional reflectance distribution function. It sounds a bit scary when you first hear it, but it's kind of simple when you break it down. There's this bidirectional part, which is basically saying there's two key vectors, there's two key directions. There's the direction to the light source that you're trying to calculate how the color, or what color is coming from that light source into this pixel that we're trying to light. So these are the two vectors, the light direction and the view direction. So you should calculate this BRDF technically for every single direction that light is coming from. And there's also the surface normal as well here. And another key vector as well is this half direction, which is calculated by adding the light direction and the view direction together and then normalizing it again. That gets you your halfway vector, which we'll see how that plays into the PBR code in a bit. Right, I think that's good. Right. So I want to show the diagrams first and then probably go into the code. So this is the normal distribution function. Doesn't have any roughness on that on this plane, so that does it good. Right, so I think I actually want to stop doing the diagram for a second. And really just show it off. Yeah. Right, so the first part of the BRDF is this normal distribution function. Wait. Something that I didn't explain about the BRDF. Why is it so laggy? So one thing I forgot about the BRDF is this is used to calculate both diffuse and specular lighting, and it adds that contribution together and gives you yeah. And also, if you remember from a light source, there's two things that can possibly contribute to the color. Is that diffuse and that specular lighting term, right? So keep that in mind when we go over these next set of things. Cool. So damn. Right, so the first one we're going to look into is this thing called the normal distribution function. We've got the debug viewing mode here, so we're just seeing how that contributes to the lighting for these spheres. And what you'll find is that this is a thing that contributes to the specular term because it's the reflectant, stuff that perfectly reflects off the sphere surface itself. So remember, if we change the roughness here, the surface will get rougher, the microfacet will get rougher, so therefore that perfect reflection of that light is not really going to, it will get bigger and bigger, and then eventually it will just sort of average out over the whole surface of the object. But I think my light is actually very intense, so really we should bring that down a bit and see it in action again. So we increase that roughness here. This really just grays out there like that. And that blue light is really intense, so we do it one more time. There we go. So again, remember, if you turn the metalness up, you will get color. Okay, I'll trim that out. That's done. Might be worth mentioning the diffuse or specularity is a property of the material, not a property of the light. I think some historical models like Fong did model that as partly a property of lights. Really? Yeah, I think it is kind of mentioned, right? Because I said when the object is metal, it will not reflect, it absorbs all the refracted light, right? I think I've mentioned that already, so I think that's okay. I didn't realize they put that as part of the lighting. Yeah, that's strange. I did not know that. Right, so I'm gonna see the diagram now, so we just do something like this. Yeah, so the diagram, there's two key things, right? There's one thing I wanted to probably do is move that pixel. Yeah, we'll do another one where we move the pixel, I think. I've got to jump into the code a bit, but it should be all right. Right, so here we're going to take a look at the diagram version so we can see it in action, basically. Okay. Right, so here we're going to take a look at the diagram version so we can see it from another perspective. So here's the value of that which comes from that normal distribution function in the code. So we have like 0 roughness here, and that specular highlight is going to be like really small, right? But as we increase the roughness, that specular highlight gets bigger, right? So here you see this number really jump up, and then as the roughness increases, you'll see here how the rays are going outside the pixels, so they're not contributing to the for this pixel anymore. And essentially it just averages out. It will average out all over the surface, something like this, where you have like, essentially you're saying like, I don't know, here we model it as a ray, but yeah, it's not as dense as it was earlier, right? So if we move around this pixel here, we're going to see it differently. So let's just watch it one more time. So we increase the roughness, it really goes up and gets very sort of dense there, and then the denseness just sort of spreads out over the whole surface of the object a bit. So we're going to move this pixel and see that in action. So let's go to that. I didn't know which one that was now. Oh, NDF. Normal distribution function. So where's pixel? Pixel. So let's move it to the left a bit. I did not talk about that halfway vector, did I? But I can talk about the next one. Like the lights had a diffuse color and separate specular color and ambient color. Right. Oh yeah, that's just to do with how you would do it in rendering code though as well. VIC. Shoot. Bit too far, but it's promising. Right, so here we've moved the pixel to the left, and notice right at the start there is no reflected light, perfect reflected light that's contributing. So notice here how we've moved the pixel to the left-hand side, and you'll see that with basically no roughness, we're not seeing any light that's contributing to, or that's the normal distribution function is not having anything that really contributes any light from the from this light here into the camera. So something that we didn't go over is there's these surface, normal, and this halfway vector, and this plays a key role into how nothing even shows up. We should move it away a bit. Move it to like 2. I'm not getting anything. Is that because the... Oh, shoot. So this is where it caps it off. But is it just, where's it drawing them? Oh, so you're not drawing them on pixel. Pause, damn it. Where's P? Oh, we pre-calculated the hit pauses. Pixel pause X plus that should do it. You're always going to get at least one ray though, isn't it? maybe we should remove that max. How do I want this thing to look a bit? So NDF was that. Right, bring this down a bit. About half, does that help? Right, so the most it goes up to is about 2. Put it 8. Not 8 eighths. Ugh. I just want to get a few little rays pop up. And maybe max it at 1. With max between 1 and whatever the other value is. Right, let's try that out. I'll do, I guess. That will do. Right, so we've moved the pixel a little bit to the left now so we can see a different angle with the normal distribution function. So if we increase the roughness here, so there's just like, you know, a tiny little amount that's contributing. So there's still a ray here, I guess, but it's so small that you won't be able to really see it contribute. But as you increase, it goes up to something that's more measurable, like 2 here, and then it will drop down something smaller. So it's way smaller than it was over here. Up in the middle it was getting like 23 or whatever. And the reason is because I was getting 23 at the peak, whereas it's getting 2.5 at peak. And the reason is because you've got this normal vector and this half vector. So the closer these are together, the more effective the normal distribution function is. So this would mean that the closer, when these things are exactly the same, you're getting that perfect reflection from the light source into the camera. So that's very obvious, right, when we talk about normal distribution, because, you know, it is basically the reflection into the camera. So yeah, that's just the way it is done with the vectors and things, which you'll see more in the code in a bit. Right, I think that was okay. Let's move that back. Yeah. So the next one is the geometry shadowing. So you should probably look at that. Okay, so we've got another specular, another part of the specular term here, which is called the geometry shadowing function. So this, when the surface is rougher, it's basically saying that the microfacet is more bumpier. So you're gonna have little hills in the microfacet, which are gonna make rays reflect off and or like and get bounced into other microfacet hills, if you will, and they won't necessarily, like, there'll be less of them, less of the rays that come from the light source itself, which will bounce nicely into the camera. Is a better way of saying it. So they'll reflect off the, yeah, they get shadowed by the microfacets themselves, or they get masked. Yeah. Right, so there's another one, another specular so there's another part of the specular term here, which is called the geometry shadowing function. So this gets combined with that normal distribution function. And, you know, the rougher a material gets, the more of it sort of like shadows, or the more darker it kind of gets. So you notice here it goes from like 1 here to 0, and that's for a perfect reflection ray, which you'll see in a bit in the diagram. But also it contributes things that are not perfect reflections more. So the way this one works is that there's the microfacet, and you've got these hills, and essentially these hills or these bumps can essentially, you can get some shadowing, so they will sort of like shadow from the light's perspective, or they will mask from the camera's perspective. So they can actually, reflected rays can get blocked by another microfacet edge, if you will, from a little hill. So we're going to take a look at that diagram now. Right, so here's the diagram basically showing the statistical sort of element to this. So you can have a bunch of rays that statistically hit this area, right, with no roughness. All of them are just going to perfectly reflect, because there'll be no little hills, which are sort of parts of the microfacet which are blocking the light from that shadowing, or there's no lights when it's reflected blocking it from the camera's angle as well. So if we turn up the roughness though, what you'll notice is that less and less of them actually, you know, more and more of the rays actually just got blocked by those little bumps in the microfacet, either by coming in from the light source itself, or bouncing off and then just getting accidentally hitting another part of the surface. So therefore it got blocked, and it can contribute to the lighting. Yeah. Is that all I wanted to say about this geometry shadowing? I think so. This, I didn't talk about the vectors, did I? Right, so this is the diagram for the geometry shadowing function. And, you know, imagine there's a bunch of rays coming from the light source, and this is the pixel that we're trying to color. So we've just got a ray coming from the camera here, and we're working out statistically how many of these rays that cover this, how much of the light that covers this sort of area, like how much of it actually ends up not getting blocked by the little hills in the microfacet, which could block incoming light from the actual light source, or the reflected light. When it reflects, it could accidentally bump into another part of the microfacet, and then it wouldn't reach the camera anymore. So with zero roughness, you'll get that perfect reflection. There'll be no, there'll be no hills that'll be blocking the light at all. But as you increase the roughness, you'll start to get light being blocked from either end, and to the point where it'll just be a smaller amount that will contribute. So essentially it's just another scalar value that multiplies alongside with that normal distribution side of things. And the thing that the vectors that are used in this formula is the normal vector and the vector towards the light source, and the vector towards the camera as well. So these are the three things that help work out this geometry shadowing function. So should we move it, geometry shadowing function, should we just move that along? Should we do that thing we did? There's that pixel pos x plus, and then I wanted to move it like, I think this could help. I want to do -2. Doesn't really, I need to move probably the light down. Yes, you're not getting any shadowing. Yes, you'll get less shadowing. Yeah, you'll get less shadowing from the light. Whereas if this is more down here, you'll actually get, oh. Maybe we should make that camera position. Bit of time. Here's one I made earlier. I did that on the Z. Nope. Alright, so I'll make it bump. Yeah, that's a really good one. Let's go get the rays. So the rays are v direction. Alright, where are my rays coming from? There. That should correct the rays that are meant to be going towards the camera. There we go, so that's good. Okay, so here's another look at the geometry shadowing. I've moved the pixel a little bit to the left, so you'll notice that this sun, the light, the direction towards the actual light source itself is actually closer to the surface normal. So you're going to get less shadowing from the light angle, right? So these rays are more likely to bounce into the camera and not get shadowed. But if the camera goes goes more perpendicular to the surface normal, it's actually going to get more masking. So less of the rays that bounce off into the camera are actually going to contribute in the end. So see here as it goes down, the amount of rays that contribute just goes further down, and that's with a very rough surface. If I take the roughness back up here, you get that perfect reflections. Therefore, there's not going to be any microfacet hills. But yeah, so as you increase it, the more likely it will. The more of the value will actually go down. All right, that's good. I like that one. Next one. Fresnel. Our buddy Fresnel. So this is where the actual color. Wait. Yeah, we want to start off with the debug view. Fresnel. So there's two Fresnels. There's one which comes from the BRDF. There's another Fresnel. Problem is the light source. It's probably better off seeing the diagram first, I'm not gonna lie. There we go. Right. Okay, so the next part of the specular term in the BRDF is known as the Fresnel term, if you will. This is multiplied with the normal distribution function and the geometry shadowing function, so they all combine into the specular BRDF. So one thing to take note is that this is where the color comes from in the metal. So you notice how the other two were scalars. This is a vector. So for non-metals, right, aka the dielectrics, these guys are obviously giving you sort of a gray color, which comes from the Fresnel term. When we bring it to be in metal, you see here it's taken the color of the. Wait a minute, why is that Fresnel 0.1? That should be red, right? Ah. Albedo. Yeah, it's not. Yeah, this is different. Right. We've got to be careful of those numbers. Because what those numbers mean is for the diagram below. Alright. Cool. Right, so the next part of the specular term of the BRDF is known as Fresnel. So it's the Fresnel function. This is multiplied with the geometry shadowing and the normal distribution function, which we just saw. And this is where the color comes from for metals, but it is where it's gray for non-metals or dielectrics. So if you take a look here, metal is 0, so it's dielectrics. This is all very uniform across the X, Y, and Z, so the RGB. And if we increase it to be metal, you notice here how it's, there's some it's different in each of the channels, or slightly different in each of the channels. Be wary, our surface color is not contributing here. The red is not contributing here. I'll do it one more time. I didn't have the red up. How long am I doing game dev for? Probably 14 years, or maybe 12 years, something like that. As a hobby, 3 years professionally. How's it going, Ty Beaver? How you been? I got way too many markers. Right, so the next part of the specular term, or specular BRDF, is the Fresnel term. This gets multiplied with the geometry shadowing and the normal distribution. And one thing you probably are noticing on the screen is this is a vector rather than a scalar. So this is where some form of color comes from. And for dielectrics, you do not get any color from here, it is gray. Whereas for the, wait, you do not get any color because it's gray. Let me double check that quickly. It's not color, it's yeah, that's that. Yeah, then the light color gets multiplied after. All right, last time. Where did you get the map from? What map? There's a map. Right, so the next part of or the final part of the specular term of in the BRDF is something known as the Fresnel. So if you're taking a look at here, you'll see that it's actually 3 channels, and so the other 2 were was normal distribution and geometry shadowing. They were scalars, and these are all multiplied with the Fresnel, with each other, basically. That should be done better. See in the background? Oh, it's a cube map. Yeah, I got it from as a resource. Here. This link. Someone's made some cube maps, which is nice. They're not HDR though, so you're not going to get super bright. You're not going to get lighting from it, but you'll get colors, if you will. You won't get intensity. Yeah, so super nice. Bit of red, I gotta remember that, and then for now, yeah. Right, so the final part of the specular BRDF is something known as the Fresnel function. This is actually, it's multiplied with the normal distribution and the geometry shadowing, right? And you'll see here how it's actually got 3 channels instead of the 1 channel. And this is because there's actually a color that comes from here. And you see there's no color coming from it right now because we are currently on a non-metal or dielectric. If we increase the metal, what you'll notice is that the red color is coming from that surface, the surface color of the color of the surface. So this is where the term which brings the color into that specular lighting. So what is Fresnel exactly? Well, we're going to take a look at the diagram because it'd be way easier to explain exactly what Fresnel is. So let's do that now. Yeah, I'm using my custom C compiler, that is correct. Yeah, this is part of the reason why we're doing this project as well, is to use the compiler and see how good the idea is, and it's proven well so far. Showing CPU and GPU code, and functions and data structures. It compiles instantly, single file with all my shaders in it. I don't have to have one shader per file. Yeah, it's great. It's amazing. Right, so here is the diagram with the Fresnel. So the basic idea is the closer the light source is to the surface and the closer your camera is to the surface, the more intense the light is going to the more rays are going to bounce. Yeah. So it's more of like the intense, because you have more of the rays which are going to reflect. Is that right? I need to look at that definition in Google again. Fresnel to PBR. What was the one I read the other day? So it's the amount of I think I have an idea of what it is. Just wanted to double check. How much reflectance was to be shown? Fresnel effect, once rendered, will add reflectivity on top of. Yes, the thing where the color comes from. But where's a simple way to say it? If material is 100% reflective, it's easy, you don't need to care about the Fresnel, but all materials absorb and refract incoming light and reflect the rest. This is either absorb or refract a portion of the incoming light and reflect the rest. This is governed by the Fresnel equations. These equations use the surface normal view direction with the reflectance approaching 100% on grazing angles as mentioned. How long did I work on HTC? 1 year and 3 months as a side project. So yeah, it wasn't too long. Yeah. So with the Fresnel, you're getting this sort of like yeah, so the light will get more intense the closer you are to the surface. Describes the object's tendency to reflect at glancing angles. It is the only one of 3 pieces that seems to have a specular word leak. Yeah, there's 2 parts of Fresnel, though. There's the Fresnel where you do the reflected ray is slightly different as well. The most explanations of Fresnel reflection flying around the internet either barely touch on a decent explanation. Yeah. Are thorough but certain lots of mass code which is unnecessary for most artists or flat out wrong. This is a particularly confusing when picking up a new package or render engine. Right. Is related to the effect that specular objects, most materials we create, where the parts of an object facing us are less reflective. Yes. The grazing angles become more reflective. In fact, at 90% angle, all objects are 100% reflective. Yes. Hey Chandu, how's it going? How you doing? We can see this clearly in nature and looking at flat body of water. So why then because in the formula I see that for one of them. Fresnel Schlick. There's so this one is view and a half. So the microfacet is facing in the half direction. And the V direction. Yes, the more perpendicular they are, then yeah, it's the half vector in this case. So the ray will, yeah, so when the more perpendicular this camera ray is and this half vector, the more the more the Fresnel, higher the Fresnel is. But why is that? Because for the reflect ray, which you see here, your Fresnel goes around the outside. That because that uses the surface normal and the view ray. And the more perpendicular they are, the more white it gets, right? So the ray to the pixel, so you can't really see it because it's the ray, yes, the pixel itself, and then the normal. So the light comes in. Oh no, but you're talking about. Right, I see now. Yeah, because you do reflect. Yeah, I know why now. I can draw it out. So you got your sphere. You got your cube map. When you have your camera over here and you're shooting your ray through it, it will hit here, and it'll do there's the normal. It'll do the dot product between these two. The more perpendicular they are, the more white, the more this would contribute. And what it's contributing is it's going to reflect this ray and then sample from the cube map up there. And that's going to decide, like, yeah, that is the halfway. Is that right? Yeah, they're always, the halfway vector and the normal always can be in the same place. That's why. Okay, I get it now. I understand now. Right, I think I can describe it. Okay, so the next, okay. Right, so here's the diagram with the Fresnel. So what you notice is the sun is on the left-hand side, shooting its ray down here, and the camera is moving closer to the surface, and also, yeah, it's going far away from the surface as well. So the two key things which contribute to the Fresnel is this half wave vector, which is again the sum of the camera and the light direction normalized, and then so we dot the half vector with the view direction vector as well. And the more perpendicular those things are, the more the Fresnel effect is gonna, the stronger the Fresnel effect is gonna be. So here we have non-metal, so dielectrics, and what you'll notice here is that the closer it gets to the ground, the stronger it is, right? The further away it gets, the weaker it is. But as we move to metals, this really will get a lot bigger, and again, the color will come from it as well. Yeah, what else do I want to describe for this one? Well, this is because see, the thing is, it's like more of the light. Is it more of the light? Is going to reflect. I think there's a diagram I've seen. There's a diagram that I've seen with the Fresnel. Like, the more of it. Yeah, those are like lenses, a lot of these. I could just brush over and just say get stronger reflection. That'll probably do. Right, so we're nearly there. We're actually close to the end now. We'll go over the code after this, and then we'll go over the image baseline. Right, so here's the diagram with the Fresnel. What you'll notice is that the sun is kind of, or the light source is closer to the ground, and the rays coming out here. And our camera is going closer to the ground and then far away from the ground. So as it gets further away, it gets weaker. The Fresnel is weaker. As it gets closer to the surface, it gets stronger. And how the maths works is you got that halfway vector, which we see again, and then you have that view direction, right? It takes the dot product between those two. The more perpendicular those guys are, the more, or the stronger the Fresnel is. So if we increase the metalness, this is dielectrics, you'll notice that it's actually grey for dielectrics. But as we increase it, the color really shows through, and the intensity also goes up as well. So what Fresnel basically is as you get closer to the ground, and the sun and the camera get closer to the ground, the more the reflected light is actually, or the stronger the reflected light actually is. Maybe we'll go and look for something close to this. Thank you, Cranston. Appreciate it. Oh, interesting. Well, this one? Reflectivity is the last one on this. Angle of incidence. Yeah, I think I was looking for. Yeah, maybe I had a different idea of what Fresnel is. Maybe. Yeah. Okay. Right, so now I'm going to dig into some of the code. So you got the BRDF. Do I just have the BRDF contribution or not? I don't really have a lighting one, do I? Could add that in maybe. So we probably want to view that. Where's the view modes? PBR view mode. Let's just make another one, let's call it light. So when we're in here, that'll be 4. So BRDF, it's already 4 should go there. 5, 6, 7, 8, 9. So what we'll do is yeah, show that and then dive into the code. We just want to show the BRDF here, so it's lighting. It's not really showing the BRDF though, is it? Yeah, showing the light. So we increase the metal. Yep. Okay, so I've got this view mode here called light, and this is only showing the lighting that's coming from the direct lights, none of the image-based lighting cube map stuff. And this is what we're going to see the code for in a second. So if this is for the plastics or the non-metals, right, the dielectrics. If we move up the metalness, you'll see here how, you're not getting any other sort of surface color appearing. So all of the other lighting really actually comes from the environment. So yeah, it's a key thing to take note. These direct lights do not actually contribute a lot to the metals. If you want to have good looking metals, you need to have image-based lighting in, which we'll look into in a bit. Right. Let's actually just get into the code. Right. So the first thing to look at is these structures that we use to pass around just a bunch of parameters, because they go into a bunch of different functions. So there's a shading strut, which has the view direction, the surface position in world space, and the surface normal as well. And then we have this thing called f0 and end.v. What is f0 again? Should probably... Yeah, I think other videos will go over that. I'll brush over f0 in mine. Right, so the first thing we'll take a look at is a couple of structures that we pass around in the shaders. So it makes it easier rather than having these massive function prototypes. We can just pass around a few structures and all the information, all the data is in there. So we have these input parameters in the shading strut, which is the view direction. So it's the normalized vector to that pixel on the camera that you're trying to shade. You've then got the surface position, so the position in world space for the surface that you're trying to color in. You have the surface normal, so the normal of the surface at that pixel. And you have this thing called f0, which is calculated internally, which we'll see in just a bit. And the surface normal dotted with the view direction. So it's actually dot product of surface normal view direction, and we max out. We have to take the maximum value between 0 and that dot product, because the dot product can return negative values, and we don't want negative values in our lighting. The next structure is this lighting strut, which has a couple of input parameters, which is the radiance or the color, and the intensity of the light combined into one. And then we have the direction of the light in world space. Cool. And the other one is the material. We'll look at that one now. And the final structure that we pass around is the material itself. This one has a vector 3 with the albedo. That's the color of the surface. We have a vector 3 for emissive. We have a float for roughness and a float for metalness. These values are between 0 and 1. Cool. Next one. So we have a function called calculate surface color. So per pixel, when you're trying to shade, we fill in those shading data structures. So shading and material rather. And then we call calculate surface color, and this will just return a color that we will then output to the screen. So we calculate the F0. This is part of that Fresnel equation, which you'll see the implementation of soon. But basically for metals you want albedo, whereas for the non-metals you basically want a very dim sort of gray. So basically we just lerp from 0.04. So there's actually some maths behind this, like which I advise you look at those other videos I've referenced. They really go over this in more detail. But yeah, 0.04 is that sort of default color for dielectrics. They actually vary just a tiny bit, but you can just default it to 0.4. There's something to look into the future, I think, for me. And then we've got the albedo here, and basically if it's metal, we want albedo. If it's not metal, we want this sort of very dim gray electric color. Then we calculate our normal sort of view, which we saw earlier. And now the next thing to keep an eye out on is the ambient and reflected stuff. We'll look at this in just a bit. But the thing I wanted to pay attention to is the lighting that comes directly from the light primitives in the game. So we only have 2 lights right now. You saw one was moving and was cyan, and the other one was kind of just white. So we have this light radiance, and we're going to go over all of our lights, and we're going to accumulate this light radiance here. So we make this lighting structure. We take that light color, and we multiply it by the intensity, and this is the radiance of the light itself. The radiance coming from the light and the direction of the lights as well. So we pass these 3 shading, material, and lighting into the calculated light radiance, and this is where the BRDF and all that is calculated. But here's our switch statement for our different view modes, and then basically at the end we take all of the radiance from all the different places, all different light sources basically. So you got that light radiance from those direct lights, and the material emissive, the albedo radiance, which we'll look into in a bit, and the reflective radiance, which we'll look into in a bit too. And we return that accumulated radiance, and that's the final surface color. So let's take a look at how we calculate the lighting radiance for direct lights. So let's recalculate the normal view. That's in shading in it. Silly me. Right, so the next function we're looking at is calculate light radiance. So this returns the amount of radiance that's come from the light, which takes into account the diffuse lighting and the specular lighting as well. So we calculate that half direction by adding the view direction and light direction, and then normalizing them as we mentioned earlier. So that's the halfway between the light and the view direction. Then you've got the surface normal dotted with the light direction, the surface normal dotted with the half direction, and the normal dotted with the view direction. and then the view dot with a half direction. These are needed throughout all of the BRDF formulas. So inside the maths equations, there's this thing called alpha, and alpha is basically the roughness squared. So you just square the roughness and pass that around. And this is where the Fresnel comes in that we saw. And with the Fresnel, so you pass in that F0, which we saw earlier, with the view dot half direction. And then you pass in the roughness as well, because roughness can change how the Fresnel works. We'll look into the implementation of this in just a bit. And you'll basically get this thing back called KS, and this is the amount of, that is that reflected light. Am I explaining this in a very easy manner? Should I probably say, I could probably break it down. I probably broke it down to maybe a bit too much. Let me just analyze it for a sec. So we've got this KS thing. You invert that and the rest. Yeah. And this is how much. Right. It's KS. This is worrying. Where's my KS? Ah, shoot. Torrents. I didn't optimize that, did I? We should pass in that for now. So I don't need the view dot half. I don't need the roughness, and I don't need the F0. All I need instead is the Fresnel. So you pass in Fresnel instead. No roughness, no view.h. Just double check that looks fine. Obviously the compiler will optimize that out because shaders all get inlined, but it's just good to, yeah, that looks the same. Fine. That's cool. Yeah, so we've got this thing. So I wonder whether I should talk about the BRDF part first. Right, let's go again. Right, so this is the calculate lighting. Right, so this is the function that calculates the light radiance and just returns the total radiance coming from the light in, or coming in the direction of the view direction. So basically at the start we just pre-compute a bunch of those vectors that we saw, right? So you've got that view direction, light direction, surface normal, and the half direction. There's a bunch of configurations of dot products here. And also we calculate the half direction, which we mentioned earlier as well. And then in those BRDF sort of formulas, there's actually this thing called alpha. Alpha is the material roughness squared, and that's passed around and used inside the BRDF. This is where we calculate the Fresnel here, and we pass in the F0, which we saw earlier, the view dot half, and the material roughness. And so we'll see the implementation of this in a bit. And then the diffuse, this is the amount of diffuse yes, this amount of diffuse. Yeah, I got an idea. Okay, so this is the calculate light radiance function. It just returns how much of the rate how much of the radiance or the it returns the radiance which is going in the direction of the camera to that pixel you're trying to shade. So at the start we calculate that half direction which we saw earlier, and all those different vectors that we have like that half direction, surface normal, light direction, and the view direction. We calculate some dot products between some of those because they are used inside the BRDF formulas, which you'll see in a bit. So one of the sort of inputs to these formulas is this thing called alpha, and that is basically just roughness squared. So you just compute that here. Then we calculate the Fresnel using the Fresnel-Schlick equation, which you'll see the implementation in a bit. We pass in the F0, the view normal dotted with the half direction, and we pass in the roughness too because that also affects the Fresnel. And we get the result here. So remember, you get some color in here if it's metal, but you get kind of gray if it's not a metal. Then we basically we do one take the Fresnel here, and we multiply with one take the metalness. So basically you're saying how much diffuse light is going to contribute to is actually going to contribute to this surface color. So the more the Fresnel is, the less diffuse light that's going to be contributed. The less Fresnel, the more diffuse light. But obviously if it's metal, you don't get any diffuse whatsoever. So the diffuse part of the BRDF is actually really simple. It's known as the Lambert term, I guess, or function. Basically, you just divide the albedo by pi, and then you just multiply KD by Lambert. And that is basically diffuse for a direct light source. And then the specular is calculated using this Cook-Torrance equation. We'll dive into the implementation in a bit, but there is actually things about the BRDF is it's built to be this flexible, there's a bunch of different implementations of the specular term and also the diffuse as well, I guess. So there's actually other methods online that people have come up with. But I'm just using the ones which are basically popular these days. So yeah, you can always research into that as well. So then the BRDF is basically just the sum, or you just add diffuse and specular together. And then this BRDF is multiplied with the lighting radiance. So remember that was the light color times by the intensity. And so that'll get you basically the color, and then you need to make sure that you multiply this with the normal dotted with the light direction, because if not, you're going to get the parts which are in shadow to the light, so they're sort of behind. They're pointing away. The surface that's pointing away from the light is going to get colored if you don't have this. So this is why you need this in here. Is it ready? Which one is the more complex one? Cecilia. Is it the I forgot what it was called now. Have you got the name? I remember now. There's a new yeah. No, if we go to the video, I think we can find it. Maybe this will ring bells for you. Oh no, we already do GGX Trowbridge. Yeah, we already do that one. Yeah, GGX something. No. Yeah, there was another one. Was it diffuse that I'm thinking of? Fresnel. Ah, it is diffuse. The Oren Naya model. Yeah, so it's the Oren Naya. That one apparently people use in film. I don't really know. Yeah, I don't know what the implementation is that. First Lambert. Oh yeah. Fair play. I wonder what the Oren code is like. It might be quite complicated. Right, only needs these guys. Interesting. Ah, JavaScript. Crying out loud. But yeah, I guess it's a little bit more intense. I don't even know if this is it. Diffuse. Require index or GLSL. Right. Right, or no, diffuse. Right, so you just divide by pi for Lambert, but Oranaya is like... So we've already got those, I think. Maybe we can give this a go. It will be more intensive though. Might look into that. Maybe we can look into that after. Yeah, we already used GGX Trowbridge. We've already got that one. Right, so this is the function that computes the specular BRDF, and it's called, we're using the cook torrents. I think it's known as the torrent sparrow sometimes. I forget. But yeah, we're calling it cook torrents. So we get the Fresnel in because that's part of it, right? And basically you're multiplying the Fresnel with the geometry shadowing function. And we use the Smith geometry, which we'll see the implementation in a second. And then for the normal distribution function, which is that nice specular highlight, we use the GGX Trowbridge rights one. So yeah, we pass in a bunch of these dot products and the alpha, and those get passed in here. And then effectively there's this sort of denominator, which is like 4 times these dot products. We make sure we max it out so we don't get divided by 0. And then we do a division with these 2 parameters here. So let's take a look at my brain. Right, so this is the cook torrents function. Remember, it's that specular BRDF term. So you pass in that for now. We also pass in the alpha, a few dot products with those important vectors, right? Those 4 important vectors. So you start off this thing called the numerator with Fresnel, and you basically just multiply them all together, which is the geometry shadowing with the Fresnel, and the result of that with the GGX Trowbridge rights, which is the normal distribution function, that nice specular highlight. So yeah, so we pass in some of those parameters there, and then basically you work out this denominator. Damn it, words. I'm trying to jump too fast. So this is that cook torrents specular term here for the BRDF. And remember, there is different ones, but we're using this one because I think it's kind of popular these days. So the Fresnel comes in here because the Fresnel is part of that specular BODF. Remember, it gets multiplied with the geometry shadowing and the normal distribution function. We're using the Smith geometry shadowing function and the GGX Trowbridge rates. So if you Google these, you can find the mass formulas online or in those videos and articles I've referenced. So yeah, the alpha and the dot products between those four important vectors are passed in here, and we pass these into the geometry shadowing and Trowbridge rates functions. So then we also calculate the denominator, which is like this 4 multiplied by these vectors here, and you have to make sure this here is maxed with a small value, so it's not 0, because otherwise you're going to get a divide by 0, and then just things won't look right when you have certain conditions. So let's take a look at those the individual specular terms for this Cook torrents. And they're right here in the right. So this is the normal distribution function of GGX Trowbridge rates. It just does that nice specular highlight rate. I'm not going to go too much over the details, but the more when it's a perfect reflection, you're going to get that nice dot that appears. And the closer you are to that perfect reflection, the more, as it gets rougher, it will start to appear on that pixel. But when you're far away from that perfect reflection, you'll only get color when the roughness is kind of gets higher, right? And it just averages out across the surface towards the end. With the geometry shadowing, use the Schlick Beckman GGX, and this passes in an alpha with an n.x, x meaning something else, because it actually is used twice. Because remember, from the shadowing function, there's 2 directions that it comes from, right? There's the shadowing, which is the direction from the light, right, with the normal. So the closer those normals are together, or the more in the same direction those are together, the less shadowing that's going to happen. But the more perpendicular they are, the more shadowing that's going to happen. Then you multiply the result of that, with the normal dot view. So this is the masking. So when the light reflects off the surface, how much does that, the more perpendicular they are, the more masking that's going to happen. So the more chance the reflected ray is actually going to bump into another part of the microfacet and not reach the light. So yeah, this just basically calculates some probability of all those rays that are in that pixel, how many of them are going to get, how many of them are going to not get shadowed or masked. And then you got the Fresnel Schlick. So it's the Fresnel Schlick version. This one takes in that F0 and a couple of vectors that have had a dot product have been dotted together, and then the roughness as well. But yeah, I'm not going to go too much over the implementation again, but it's the more reflected, the more perpendicular. Okay, we'll do it again. Right, the final one is that Fresnel Schlick. So it's the Schlick version of the Fresnel term we're using. So you pass in the F0 the dot product of 2 vectors, right? It could be, because it's used in 2 different ways in the overall PBR lighting, which you'll see the second one soon, and some roughness as well. So this is the one which has been modified with roughness. You will see a version without this. So I'm not going to go too much over the details again, but the more perpendicular that the 2 vectors are, the more the stronger the Fresnel is, right? The less the less perpendicular they are, the less the Fresnel is, right? I remember this is F0 is going to have more of like a color if it's metal, but if it's non-metal, you're just going to get a gray, right? A very dim gray that comes in here. Right, that was good. I love how this is laid out, by the way. This is most readable PBR shade I've seen. Thank you. I think some people disagree with all these sort of like vector things, but I find it readable. The first version that I did was very messy and there was no reuse anywhere. But then I managed to, yeah, I took time and cleaned it up because yeah, I want it to be readable for me later because I actually want to come in here and you know I don't know if I'm going to keep this when I do a second pass of how I want things to look because maybe I want to do something that's kind of not realistic. I don't know, just tweak some bits. So it's good to sort of have in a very understandable format, I think. But yeah, right. So that was that. That's the direct lighting, isn't it? Yeah. So there's only two more things to cover now. Yeah, exactly. It's good to have. It's way better than what it was. It was used to be horrible. It's just basic n.l multiplied by that and done. Right, so going back to that calculate surface color. So all the stuff you're seeing for now is the direct lighting from those fake light primitives, right? But the thing is you're not going to get any, for metals at least, you're not going to get any other lighting and it's going to look horrible. And plastics, it will kind of look okay, but you're not going to get that nice reflection in the plastic either. Or there's also going to be a dark side of the sphere or the dark side of your surface because you're only getting the direct lighting and you've done the n.l, right, multiplied with the normal dot light, so that the normals of the surface which point away from the light, those are not going to get any lighting from the overall environment. So realistically what you'd do is you'll shoot rays, a bunch of rays all over the hemisphere, and you'll collect all of this, all of the lighting from the scene, and then that will contribute to the lighting for this pixel. But that's really expensive, and you can't really do all of that per pixel. So we actually pre-calculate it, and we use some environment map to pre-calculate it. So we're just going to go over how you use it inside the shader, and then we'll look into the actual different environment maps that we have created. So there's this thing called ambient radiance. This is diffuse light. So we need the Fresnel here, and this Fresnel is a bit different. It uses the normal dot view, and this is because the normal is where the half vector would be when you have a reflected vector. So you get this KD, which is basically saying how much of the diffuse light do we want to contribute to this shading pixel, and then we sample from this thing called the irradiance map. So the irradiance map is a pre-calculated color, which is based on the surface normal. So it's a cube map, and at the surface normal we store a pre-calculated hemisphere rays count. I want to describe that one again. Right, so we're looking back at that calculate surface color again. So this is the entry point of everything that we've seen. So we looked at the direct lighting. So you're just going to see the lighting that comes from the direct lights. So it's going to look mostly okay for the plastics, except for there's going to be a dark side because you've got the normal dot light direction, and so you would not see anything that's not directly lit. And then if you move over to being a metal, then you're just going to see basically the normal distribution function. You're not going to see any sort of surface color at all. So that really all comes from the reflected light, because again, the metals only show reflected light; they don't show any diffuse light. So direct lights will only give you that sort of the light that comes directly from the light primitives itself. So what we actually need is the lighting which comes from the rest of the environment. So we have a cube map, which is seen in the background, and this cube map is kind of the rest of the environment. You can do some more computationally expensive things later, but for now you can just do image-based lighting and it just gets you up and running, and you can tweak it more later on. So there's two key aspects. There's the ambient radiance and there's the reflective radiance. Ambient is diffuse, whereas reflected is specular. So we need to do a Fresnel here. We pass in the F0 and the n dot view, so normal dot view direction, and we use the normal here instead of the half direction because the normal is the half direction when you have in terms of a reflected ray, right? When you're reflecting the view direction on the surface normal, you're going to get, and the light that comes from the reflected ray, those two added together normalized gives you the half direction. So what we have here is we calculate that KD, which is the amount of diffused light that's going to contribute to this pixel here, because if it's on the edge, you want more of that Fresnel, which is more of the reflected radiance rather than the ambient radiance, right? Which you'll see in a bit. So basically, we have a pre-computed cube map, which has all of that ambient radiance stored in there. So all we need to do is just use the surface normal just to simply look it up. So it gets stuff from the cube map, but not necessarily stuff. It's directly neighboring things. So if you want stuff to be really correct, you need a more complicated solution. But for now, this will do. And then we take that irradiance. So irradiance means it's the amount of light that comes from all around, whereas radiance means it's the amount of light that comes from a specific direction. So we'll see more about that in a second in a nice diagram. And then you multiply the albedo of the surface by the irradiance, and that should diffuse. And you do that Lambert thing again. Actually, no, you don't do that Lambert thing. You just multiply the diffuse by the KD, and that is your ambient radiance. So let's take a look at the diagram for the ambient radiance now. Right, that was cool. Diagram time. Right, so we have another diagram here which is showing how a cube map is constructed. So this cube map is much lower resolution, and this stores the irradiance for a given normal. So basically, cube map can be thought as something which is like infinitely far away. You can you can move around inside cube maps and that, but we don't really do that. And also you could probably like blend between a couple of cube maps or whatever. But again, we're just keeping it simple, and we're just imagining that for every single time we hit a surface and we get a surface normal, we're just going to imagine they all point in the exact same direction and hit the cube map in the same place. So with this ambient diffuse color, the way you need to produce it basically is you need to shoot a ray. So you take your surface normal and you shoot a bunch of rays around the hemisphere. So you don't shoot them under the hemisphere, because that's going to be where the surface is, and you're not going to get any rays that come under and then reflect into your view direction. So basically, we pre-compute a cube map where for each pixel here, so we've seen this pixel here, we are taking the normal towards that pixel we're trying to shade in. We shoot rays all around, and we sample the big environment map, the one that you're seeing in the background here. And you get all the samples, you take the average, and then you store that in this pixel. So the next time, so when you look at this pixel inside the PBR shader, which we just saw that ambient radiance, right, or that irradiance, we simply just look it up, and that's a pre-computed value of all the irradiance. So let's take a look at the view debug mode again and see how it looks. Right, so here's the ambient color. So because it's a very dark scene, we're going to have very dark colors. But you'll notice that it is kind of a little bit brighter underneath, maybe, because of those other lights, and maybe it's a little bit darker on top. So we can actually open this up in the screenshot viewer and see that a bit more. So let's do that now. Right, so here's the screenshot viewer. So we're going to increase or decrease the white levels, and you'll see here how it's brighter here but darker on top. And then what else do we need to... Oh yeah, now I want to show... So this is what the irradiance map texture looks like inside our texture viewer. So we have 6 layers, right, one for each face of the cube map. So we're just going to cycle through those now. You see they're a little bit different. This one looks like the top, it's darker, right? And yeah, so there's just a bunch of different layers. And remember, it's much smaller resolution. This one is 32 by 32 pixels, whereas the environment map is actually 2K per dimension. Or just a 360 cube map. Or just a 360 cube map shot. Actually, a special thing, not just a cube map shot. It's 180 degrees from a surface normal. Yeah, they're not too bad to implement actually. But yeah, the irradiance map. Yeah, because typically you'll have like, yeah, it just allows you to get a bunch of like, what's the general color of the scene, average color of the scene, and contribute that to every pixel. If that makes sense. Right, so here's the dark patch here that I'm talking about. When we then apply all of it on, right, you'll see that you get the ambient color, but it's also, you've seen the reflected, which we haven't covered, but we'll be doing that in a second. Right, so for reference, I actually used the OpenGL or the learnopengl.com tutorial here. I froze. My face. Right, so we're actually using the diffuser radiance tutorial from the Learn OpenGL website. This is the one that I actually used to get this up and running. So hopefully that diagram that I showed just gives you a good basic idea of how, you know, to approach this thing. And then also use the specular IBL as well, which is for the reflected ray, which you'll see in just a second. Oh, and also that blog post that I shared as well, the image-based line with multiple scattering, also covers that diffuse and specular one in a slightly different way. So I highly recommend you read through this as well and look at the image-based lighting section here. Right, just the reflected irradiance next. I've only seen shaders that use raw captures environment without any calculation. Yeah, I guess they pre-calculate it. I imagine. Yeah, they probably recalculate it. Metallicness, I think they lap it with roughness. But yeah, that's correct though. Other than that. Um, right, so the final part of this surface color that we didn't go over is the reflected radiance. So this is that specular contribution from the rest of the environment that's not the direct lights. So you calculate the reflected ray direction using the reflect function. You have one in GLSL, you have one in HLSL, I think. If not, there's maths out on the internet. Find the maths and use that. It's the negated view direction. So remember, the view direction is towards the camera. So it's the opposite of that. It's towards the surface instead. And the surface normal, and that will get you the direction in which it's reflected. Like a perfect reflection. And then we sample from this BRDF texture installs an average of a BRDF that's been pre-computed. That's in the tutorials for the OpenGL stuff, which you'll see, or the Learn OpenGL tutorial. And then there's the reflected radiance, which comes from another cube map. This one is the same resolution as the actual cube map environment, but it's a different one called a pre-filter map. I might change this name later. I'm not really a big fan of the name, but yeah, it's called a pre-filter map. It's another cube map, and you sample it with the reflected direction. And then it has a bunch of different MIP levels based on the roughness. So as you increase the roughness, you want to get a blurrier reflection, because you're not going to get your rays perfectly reflected. You're actually going to get more, a lot of those rays which come from the light source are going to be, or the environment in general, are going to be bounced at different angles, not perfect reflection. So you just basically storing a pre-computed version of that in that cube map, which we'll see the texture viewer and the game in a second. And then you take that Fresnel that we saw how much specular light is being contributed to this pixel, and it also has a bit of color in there as well if it's metal. And we multiply it by this BRDF X, and then we add the BRDF Y. Again, don't be too worried that you don't know much about it. It's all in the blog post and the blog post that I've linked. And then we multiply that BRDF. So it's just another bidirectional reflectance function, which we saw in direct lighting, but just here. And then we multiply it with the reflected radiance. So let's take a look at the scene and just see how this contributes to the picture. Oh, the diagram. Yeah, I want to see the. Do you want to see the diagram? Right, so here's the reflected view mode. So we're just seeing purely what the reflected view ray gives. So remember, every pixel we shoot has a surface normal, and we reflect the ray, and we sample from that new cube map called the pre-filter map. And it has MIP levels based on roughness, which we'll see in a bit. But remember when we had that Fresnel term, and that Fresnel term, when it is a dielectric, it has like a 0.04 color, doesn't it? So it's not going to get that strong of a reflected color. But the more metal it is, the more reflected color it's going to get, right? And just to have a bit of a look at the Fresnel, this is the Fresnel term for that reflected ray. You'll see here how it's brighter around the edges, right? So it's more brighter around the edges here. And when we look at overall, you'll see here that you get this nice, like, strong reflectance around the edges, and that's purely comes from that reflected ray and reflected specular, and that's thanks to the Fresnel So let's take a look at the diagram and then the cube map. I feel like this video is getting better as it goes on. It's fine. Right, so this cube map is the same resolution. So it's not a smaller resolution like the diffuse one. This specular, this reflected cube map is the exact same resolution as the environment map. And it works in a very similar way, how we have a pixel and then we have this normal vector, which is just from the middle of the environment. So every time we have a reflected ray which just goes in that direction, we just use that. We just take this pixel, which has all the pre-calculated reflected information in there. So when we have a roughness of basically zero, we just shoot a bunch of rays going forward, and we average the color out from the environment map, and then we store it in that pixel there. And then as you increase the roughness, these rays get wider and wider and wider to the point where it basically becomes like a hemisphere, right? A little hemisphere. So let's take a look what that looks like when you have your pre-filtered map in our texture viewer. So here's what a pre-fill map looks like. So it uses this thing called importance sampling. So you don't really get like a sort of downsampled looking image. You get a really nice blurred image. And it's kind of interesting how this is at zero roughness, right? This is the MIP level at zero roughness. It's kind of interesting how that reflected ray still kind of looks like a perfect mirror, even when you have a little bit of roughness. Yeah, and the MIP 0 kind of looks like this. So let's just increase the MIPs. This gets blurrier and blurrier and blurrier. So as the surface gets rougher, we are going to sample between two different MIP levels, and it will interpolate for us, right? That's how the sample code works for GPUs. Because it gets rougher and rougher and rougher, basically, and obviously lower resolution. So let's take a look at some of the code, I think, and just so you guys can have a reference to how my code works compared to the tutorials. Right. Yeah, I think I just want to show those two shaders off. So it's like the render irradiance map. Right, so here's the render irradiance map. We're using a compute shader, so just launching per pixel, and per pixel of a cube map face, and we launch this shader for every single face of a cube map. And basically we get a normal, right, towards the pixel that we're trying to render into this frame. So it's from the center of that cube map. And then, you know, all this code basically comes from the Learn OpenGL stuff and that blog post as well. And this is just the for loop that computes the hemisphere. So we're doing, I think it's, yeah, we're doing like thousands of rays per, you're doing thousands of rays per pixel over the hemisphere. And then we're counting how many rays, and we're accumulating the irradiance. And then at the end, we just essentially work out the average of that irradiance and then store it inside the texture at that coordinate. It's all cached, so we don't have to do all of this calculation per pixel. So yeah, we're just sampling the environment map at MIP 0, like so. And something to be aware of is, since this is a low resolution resolution version of the environment map, we actually, you know, you got to make sure you get your faces right, because it's really easy to sample the wrong face and storing the wrong face. So one nice bit of debugging thing you can do is just output like a low resolution version of the environment map and just make sure all of your cube map faces are in the right place, basically. Right, so let's take a look at that pre-filter map. This one is a little bit more involved. It does some thing called importance sampling, but again, the same sort of debug thing applies. Make sure you got your faces set up in the right direction with that by just reading from the cube map and this output, putting it into the new cube map. But it's a similar sort of thing where we have a normal going towards the pixel that we're trying to render this frame. So yeah, we launch a compute shader the exact same way, but it's a bigger cube map this time that we're rendering to. So it's more expensive. So you just take a normal from the center of that cube map to the pixel that we're trying to render for. And again, I'm not going too much into the details again, but there's a number of samples. There's a number of samples basically, and how rough, depending on how rough it is, depending on how more spread out those samples are. And then that is all worked out based on this like importance sampling thing, and all that code is available on the on those blog sites there. And another key thing to take note is that this pre-fill map shader is also launched per MIP level, because there's a MIP level for each roughness as well. Yeah, I think that's it. Right, that's really good. Right, what I think we should do is I want to record the end of the devlog, and then I want to record, and then we can try out that Orania diffuse, because I haven't tried that out, and it is more complicated, but I just want to see how it looks, right? So this is instead of Lambert diffuse. I wonder if that MIP roughness here is correct. Like you said, it should be the same as the environment map. Oh no, yeah, it is correct. So I used to have it as a perfect reflection. But the problem with that is that if you have something that's completely no rough, so if you look here, it's kind of a bit blurry. I think I want to, yeah, so I think it's something you should tune, because if not, you will get perfect, like you'll get perfect reflectance or whatever. And when you're far away, right, which my game is going to be far away, you're going to get more shimmering. Let's remove that anti-aliasing for a minute, that anti-aliasing bug, because we've not quite anti-aliasing anymore. But yeah, you're going to get perfect shimmering. So I think I should mention that. Yeah, you'll get really bad shimmering on the surface, but we're not getting shimmering here, right? Because we've made that a little bit rougher at MIP 0. Yeah, I think I should say that. Right, so one thing to take note is, if you remember that the sort of specular pre-filter map thing, that reflectance map that we saw, that MIP 0 was really blurry. And if you see here, this is basically roughness 0. It is a little bit blurry, but it's not like super blurry. So the reason why, so I think I've tweaked my numbers a little bit. So I've made the base MIP a little bit more blurrier, because for this game, I want it to be sort of more zoomed out. And when I was more zoomed out, I was getting some very jumpy pixels, like things were just bright and then not bright, and it was causing a lot of flickering. But now, because I've increased that roughness just a little bit for MIP 0, you're still seeing it reflected at this distance, but you're not getting it like flickering and causing these really jarring like artifacts. So it's really something you should play around with when you implement it in yours. But you can always just make it a little bit rougher. Because I'm doing ray tracing, it's hard to get the derivative. Maybe you could just increase the roughness based on the between 2 pixels. What's the difference between between something like the UV or something like this, and use that to calculate the roughness, perhaps. But yeah, it's something we're gonna play around with in the future, I think. I remember now. I suggested biasing the MIP based on f-width. Yeah, but of course it's not really viable if we don't use a ray tracer. Yeah, there is some papers on. Sorry, with rasterizer. What you were saying. Yeah, there are some papers if you use a ray tracer like we are, how you can calculate that derivative. But yeah, I think we'll have a bit more of a play when it comes. Maybe biasing the distance based on distance squared, which is measured with the area of pixel covers. Yeah, actually, since I'm doing it, I think I'm doing like a fixed camera, kind of like up. So maybe that will work because, yeah, because everything is probably going to be about the same size. The problem with that method, I think, is that if your smaller and bigger objects will behave differently, I think, right? But I think they're all going to be about the same size. So I think it should be fine. But yeah. Man, I got like a bajillion markers in this. I hope future Henry can edit this video good. Yeah, what else did I want? Oh yeah, I just want to do an outro and then we'll do that Orania implementation and see how much better the diffuse lighting looks. That'd be interesting. So I got a lovely LibreOffice presentation slide. Right, so this was day 21. Right, let's check the VOD channel. By the way, guys, we have VOD channels. You should check those out if you're interested in past streams. But we also have a YouTube where you can watch these devlogs that we've recorded. Usually they're just cuts. Usually I just cut up the streams and put them into a devlog. The PBR has just been something I've been learning, so I didn't want to cut up me just failing and being confused and do more of a version of me which kind of understands stuff more and kind of break it down a bit. Yeah, so it's from 120. Oh, did I already change it? I already changed it. I already recorded it for PB. Yeah, exactly. Manually calculate it, but we can't calculate because we're using ray tracing. It's a bit harder. Wow, my last one got 600 views. How did that happen? I guess it's font rendering and everyone trusts a bit of font rendering. Interesting. Huh. I'll take that. But yeah, so it's right. Right, let's do a quick outro and then we'll do the Orania. Right, thank you everyone for watching this video. This is devlog 13 and it is actually from day, 120 to it's about 5 later when it's about 125. Yeah, 6 layer. Maths. Something like that. Right, thank you everyone for watching. So this is devlog 13 and you can catch the streams on the VOD channel, which we'll see in just a second, from 120 to 125, something like that, where we actually did the implementation of PBR, if you want to see it more in depth of me going along and trying to learn it and implement it. But if you guys want to get access to the source code and have a play around with the actual repo that we've been demoing here, and maybe I didn't cover everything to the detail which you might have a question about, you'll be able to play around with the code on a Windows or a Linux machine. Damn these words. Linuxes. Right, thank you so much for watching this devlog, guys. So this is devlog 13, day 120 to 125. You can view those on the VOD channel if you want to see it more in depth of me trying to figure out PBR and the steps I sort of took along the way. But also, if you want to get access to the source code, you can subscribe via Twitch or Ko-Fi. Ko-Fi is much better for me. More of the monies goes in my direction. But the source code would be very useful if you're interested in playing around with the repo and, maybe I didn't quite cover it in the detail where you might have a question around. And you'll be able to sort of have a play around in the code base and see for yourself what the answer is basically. And yeah, so thank you for everyone who's supporting me there and doing so already. Really appreciate it. There's a VOD channel on YouTube. You can check that one out and see the VODs, any past VODs. Got lots of cool stuff on there. And the Discord if you're going to come and hang around in the meantime. Right, thank you guys. See you in the next one. Right. That was good. By the way, have you tried Shafiroforia's video editor? It made specifically for cutting down. No, I haven't seen this. Right. Yeah, I just use Kden Live and I've got the markers and I just sort of like have my web browser open with the Twitch thing and I just get the timestamps and just go and cut it. What's the goal of the art style? A bunch of balls. Maybe not balls anymore. Might get slightly different shaped balls, but have you got a link to this guy's editor? I never knew this was the thing. Right, so we're gonna look at that Oranyaya diffuse. Maybe interesting. Oranyaya diffuse. It's apparently what they use to be more realistic. Oh, this guy, I've seen this guy around. Oh, he's actually made. Oh, he's the Zig guy, isn't he? Is this Zigware? It's Zigware. That's cool. Yep, politics. Streams provide long videos. Maybe short videos are better. Cutting stuff down is hard. Can we make it easier? Current state. Functioning enough. Seek by auto-generated subtitles. Select selections, quick drag. Ah, auto-generated subtitles. Nice. Right, I wonder how good this works overall. But yeah, mine's not. I need to cut down. Wait, do I just cut down these days? Yeah, I cut down boost levels. So maybe this is not exactly what I need yet. But as it gets more functional, this might be good. Because I need to boost the audio. No, I don't. Maybe it's fine. Yeah, I might look into it. Thank you. Do that on Twitch. Oh yeah. Yeah, the balls are stack. Thank you. I'll take a look into it. Right. I'm just going to take a quick break, get another drink, refill, and then we'll do that Oranyaya diffuse, which is different from the Lambert diffuse. And apparently it's what they use to be more realistic. We'll see how it looks. We'll have an option for it. It'll be cool. Right, so BRB. Right, hello everybody, welcome back. How are we all doing? Yeah, so let's take a look at implementing this Oranyaya. It's probably Oranyaya, but anyway. Oranyaya. Right. Diffuse. So, yeah, let's get some code. So usually use that Lambert, right? Remember that? Lambert? Yeah. And it's usually just albedo divided by pi. Bit of pi. There is roughness here. And I was told to be careful about roughness using the same specular roughness with diffuse roughness. So maybe we don't do that. But yeah, let's bring this in as a thing. Where's the albedo, a bit of pi. There's a pi in there as well, right? So there's a bit of right? Okay, gotcha. STs. Yeah, so that was said by. It's in video form, so if you're a Gen Z, you're gonna love it. It was said somewhere around. I watched this video so many times. It's probably from here, in this section here. Yeah, it's when he talks about, it's somewhere around this part here. Maybe, or maybe that's the subsurface scatter. But yeah, it's somewhere in this section. 14 minutes to either, I think so. Yeah, he mentions about you can have roughness. Or maybe it's later in the mathematical model section. Yeah, I don't quite remember. But yes, I'll relink the video just in case someone is joining and seeing it. Good video. PBR, all the maths about it in a nice single place. In a video form, you can watch it like 10 times and learn every time something new. Right, bit of Oranyaya. The Lambert is like so primitive in comparison. It's just like, hey, divide by pi. Whereas the Oranyaya is like, you divide by pi, but there's a bunch of other stuff to be concerned about. You're like, oh. So this is interesting. 1, 2 spaces, ooh. 2, GLSL, ooh. Roughness, albedo as a float? What spaceship are you on? What? That's just going to be grey. Right, I guess you just put in a float, vector 3 instead. I might look at another implementation. This guy just screams JavaScript. Right, let's keep all this light viewed surface normal. Don't know why I'm cleaning it all up, but Right, so where's the floats? The vectors, if you will. So we just dot those boys and girls. Right, so the only other one to worry about is the albedo. So that is here. Right, we've got things to be concerned about. Not simple scalar maths anymore. I guess I could say ARGB. You know, I'm gonna find another implementation quick. There's a link. Ew. Ah, amazing. Disney, physical-based rendering. Renormalize Disney, moving Frostbite. Right. Improve Oranaya. Fast Oranaya. And then normalize Oranaya. GGX Oranaya. GGX approximation. Interesting. Lambert, Disney. Crying out loud, there's so many. Oranaya. And just keep stuff still, man. What's going on? The roughness doesn't play an effect into this one. Oranaya does though. Physics. Yeah. It's the same. But as roughness increases, yeah. The metallics obviously don't get any diffuse. The GGX approximation, what the crap? That one looks weird. GGX Oranaya. Is that real? It's oddly dim, but this is just diffused though. You get the specular bits still. Right, it's like a Disney one. Interesting. Yeah, I wonder where... Yeah, it's interesting. There's more. Oranaya. Wait, did I close it? Let's get over here. Why have I got these tabs open? I'm becoming that type of person. So there's like the GGX Oranaya. What does that look like? There's the albedo. Yeah, it won't run because I updated my browser. See, why is A albedo A? Why is it just a single thing? That doesn't make any sense. Albedo A. It just returns a float. They didn't need grayscale. Bastards. They just like doing it grayscale. But yeah, we can always just change the other version that we've got. Anyway, there's another one I wanted to look at, which was that GGX Orinoya. What? The Orinoya Archives. Yeah, it seems like a good diffuse, a better diffuse might be the next way to go, I think. Right, lots happening in the graphics community a lot of personal news, especially when it comes to physics-based rendering. That become popular in 2009 as hardware become more powerful models. Sorry, as hardware made more powerful models affordable, and really took over between 2010 and 2014. Rotom engines started replacing Fongline and Blimfong with normalized Blimfong. So pretty much everyone switched to GGX and its long trading reflections. Researchers explored how to make it work with image-based lighting, area lights, and nowadays everyone is looking at the secondary bounce problem. I'm not sure why the adoption also happened at the same time in the film industry instead of much earlier, despite having different constraints other than real time. Interesting. Films made before 2010 were mostly ad hoc until a wave converted nearly the entire industry to unbiased path tracing. Oh. Right. Anyway, TLDR. I ain't got all evening. What is NPR? Give me the juicy details. Disney and the BRDF. What? Is there so much? Right, diffuse. Yeah, there's this GGX one. Non-photorealistic rendering. Yeah, the thing is though, you can do both, right? People are mixing both nowadays. There's a GDC on it. Oh, is this the L guy from GP Gems? Interesting. Key takeaways. New diffuse equations derived from the same assumptions as GGX Smith specular. Whoa, mind blown. So, new cheap and good shadowing masking. Right. Some discoveries on the way. Why is that 4 in specular, PBR specular? Right. Oh, interesting. Um, uh, 'I'd love to watch a video on this, but you have to be. I've got I've got a login though through work, so I can always just look at that, learn more. Powers and lerps n.l. Yeah, see, we're probably gonna be doing funky little stuff like, making it incredibly incorrect later. But yeah, it's a good idea. Like I think PBR is a good base, and we want to obviously stylize it to something like make it completely, yeah, just butcher it a bit, you know. I thought there's some easy code somewhere, but not really. But that's a lot of slides just for diffuse PBR. Yeah, it's interesting. Yeah, there's like a GGX or a Naya somewhere to be found. Is it on shader toy? Super fast GI or no? Eh, maybe. Are you sure it doesn't contribute? Nice. Where's the Oren there? Oren. Great. Probably uncommon in it. Right, I can see this being readable. Yeah, I ain't gonna be able to decode this. Anyway, it's worth a try. Let's have a gander and decode what you're saying. Right, I'm gonna change this. We're just gonna use this one, but if I take a look here, so diffuse, ambient, right? Light diffuse. You see that's diffuse. So for your plastics, yeah, obviously for plastics it only matters. Metals it won't. So yeah, it's going to contribute, man. It's going to be different. We won't be able to see the toggle. RNI diffuse. So I've got to calculate this damn albedo thing. Wait, just return to float. There's an albedo that goes in. See, most of them don't. See, they passed in a float. For the two implementations I've seen, it's just a float that goes in. So, and they call it albedo. Albedos are 3 channels. So, the part that I'm confused about is the albedo divided by that. Yeah, they must have just been doing it. Well, let's just do it grayscale. I've got a luminance function. And let's have a bit of a play. Naya diffuse. And we're just throwing a luminance. Right, splat. Light direction. So we should already pre-compute all those, but lighting dot light direction. View direction. Surface normal. Roughness. And then albedo, so GPU luminance from the color So yeah, obviously dinner luminance is wrong. We should probably pass in the whole color. But let's just see how it looks. And maybe we could do a toggle. Maybe we could say, hey, if the probably something we can use. We could say if your roughness is completely 0, use this one or use the other one. Yes, we could say, hey, if the roughness is completely 0, because the roughness doesn't really play a factor into the Lambert one. So we could say, hey, if it's just completely 0, then use Lambert. If not, use Oranaya, and that way we can just compare it. So yeah, we should probably make it. No, there's not an instruction for it. It's just quite. It's just this, right? You're just multiplying red by a fraction, G by a fraction, blue from a fraction. So green is the brightest color, red's second brightest, and blue is the most dimmest. But yeah, I got these values from some implementation online. Yeah, I added it actually off stream to do the diagrams, because the diagrams needed illuminance for some reason. Bit of a step. Oh, there's a bunch of damn doubles in here. Mix. Lerp. Not like it. Mix. What's going on? Right. Cool. Let's test out this Oranaya thing. It's going to be grayscale, but wait. We've got to make this one grayscale as well. Hold on to your horses. Luminance. Lambert. Oh, Jamega, how's it going? How you been? Has been a while. Material X as an implementation, the first one. It doesn't take albedo, it just multiplies that after. I was thinking that could be possible, but then I thought no, because it's passed in and used for the division. But maybe. Thank you so much there, Isaac. Appreciate it. Well, sorry. Isaac. Isaac, innit? But yeah. So that's, okay, so there is a difference, right? Let's go to the diffuse. So this one's Lambert. And as we put the roughness on, that's Oranaya. So it is different. You get a nice sort of shade on the, you know, where's this other light? Get rid of it. Yeah, so you get this nice sort of like, nice fade with the, with that edge there, if you will. So the light's coming from up there, right? So that's kind of nice. And then as it gets rougher, it kind of changes too. Interesting. Right. Oh, meh. Bunch of layoffs gonna go on at work. Crap. And I hope you end up surviving that, because that really sucks. Especially when you just moved here to set up and everything. But I hope you find out, you know, Find out soon, and hopefully survive. But yeah, it sucks either way though. If it's you or other people getting laid off, it sucks either way. Um, yeah. Um, yeah. There's not much else I can suggest. Yeah, I think there's like a position going on where I work, but it's for a principal rendering engineer. So yeah, it might be. I'm sure you could do it actually, because you're a wizard. But yeah, you might have to convince other people. Official PR, 10%, but that's like 1.5k person company. Yeah, it's like over 100 people in it. A lot. You can do luminance with a single instruction with phase and dot. Ah, of course. Maths. Yeah, this compiler should sort that out. But yeah, that's a good point. Just dot it. Yeah, I guess it's an instruction, but it depends if they. Maybe they might do it as an instruction. Maybe not. Yeah, that RNI looks like way better, doesn't it? Let's look at that Material X implementation. Right. Material X is the AMD thing in it. There's different versions. I would shake my screen right now, but it's a new screen, and I like it. Alright. What are all these bells and whistles for? Ooh, surface scattering. That's something else to do in the future. Maybe. RNI diffuse albedo Monte Carlo. What? Ah. Yeah, because you need to do it for the other things as well. The other shaders. If you need the incoming directional light. Right, so if I do a bit of RNI. Right, it actually looks. Right, I got this. So we're passing the albedo. So those end.ls and all that. We've already got them up there. So view light, view half, view light, light normal light. Alright. Hold on. Right, n.l, n.v, l.v. I don't know if I've done that one. Right. That ought to be good enough. So we should be able to l.v n.l n.v. Right, so the reason why I didn't think you could just multiply by albedo later is because there's an albedo here divided by here. So I'm like, So what did they do in that then? Sigma 2 plus this. Those scalars are a bit different. Right, this is a bit different. But that's cool. Let's roll with this. whatever. This is way less computationally heavy. Let's just port this version. L dot v n dot l, crying out loud, n dot v. Let's get rid of these damn doubles. Square. Kind of nice having a square function. Sometimes when you have expressions and that, you don't want to put in a local. But it's kind of useless like that though. So what I'm thinking about doing is take this, just multiplying it by albedo and returning that. Mul-s. Let's call it. Already got one called s though. Albedo. I don't know. Call it R. Mystery R. Right. Ornyaya. Use. Rightio. So, no longer do we pass in a silly luminance value. We're passing in like what again? N.L. I forget these. Yeah. N.L. N.V. L.view. We don't have that at the moment. Right, that's good. So let's remove the luminance thingy, which we... Right, so now we should be able to compare Lambert to this one. Or yeah. As I see it. Oh, there's no square, is there? I thought I had a square function, but anyway. Oh yeah, bit of R. Yeah, they're scalar and vector. Yeah, I think they have a dot product instruction in SPIR-V, but that gets lowered into individual scalar operations. Because the problem you have to solve is you don't want to recalculate the same expression twice, right? So if you have x x plus another x, right, or whatever it is, and hey, wait, what is it? It's the dot product, isn't it? So it's multiply. Yeah. It's x multiply x plus y plus z multiply z. And those results of x times x and y times y and z times z. If those ever get reused again, you kind of want to save recalculating that. Like, and yeah. Unless there's a way to do it in hardware where it's just cheaper. Yeah, so I don't know. Yeah, apparently I don't have them. That's fair play. I don't know. Well, that instantly looks way better. Or different. What I just said better without. Yeah, that just looks different. Let me think about it for a minute. Here's Lambert, and this is with. Right, really ends up being a bit brighter. So I've got big intensity. Let's bring the intensity down a bit. So if I go, yes, Lambert's a lot dimmer. As I increase it, so Lambert's at roughness 0. Then as we take it off exact 0, right, it ends up being a bit brighter. We've probably not got the divide by pi in there. Ah, thank you. Yes. Similar trains of thought there, that's good. And the n.l for the complete BRDF. Interesting. Right. You need an n.l in there as well. Oh yeah, there's already an n.l in there anyway. That's done. Yeah, that's done at the bottom here. Right. But then, cool. But we were saying you want that divide by pi. Yeah, it should be the inverse pi though, but YOLO. YOLO. Yeah, inverse pi is actually way better in it. Right. Now before we say better, let's look at it and see how it compares. So, roughness 0, Lambert, bit of Oraniah. It's hard to see those the anti-aliasing is kind of off. I can't really see too much of a difference, but I think you see the difference in the right diffuse. I thought we saw that the why aren't I seeing the thing anymore? This used to look way better here in the other implementation. But we are seeing this though. It is getting a bit dimmer with the rougher it gets, which is kind of, you know, get rid of that other light. It's annoying. But yeah, when I did that other Oraniah, this had a nice fade to it. Yeah, I guess it's more correct, right? It does look a bit different, but it's a lot more maths, and you don't really get much of a difference with this one. The other one looked better. Still has specific VOEs, right? NVIDIA's latest hardware doesn't. Oh. Interesting. So what? So on the sim. So they don't have. Are you saying they don't have a scalar VOE? They have a arithmetic unit for both the shared one for scalars and vectors. Is that what you're saying, Jomega? Yeah, I don't know if I like this version. It really doesn't. Like the other one, it was just better. But yeah, let's get back to that old one. Crying out loud. I gotta copy paste it. So this is the other one that we found. Let's get it in here. To the top again. So this one, it is albedo divided by this. What's that? I could take the luminance just to get it working. And then monkey around with it in a bit. Let's just do luminance. Because then it's just become a scalar. Right, let's try that now. And right, more or less. What? All right. Right, let's have a look at that. Yeah. So this is Ornaya, Lambert, Ornaya. So it really has a bit of a difference. It's more softer as well. Like you're not seeing a harsh edge. Yeah, I think this version just looks way better. Let's get rid of that blue light. That's annoying. Yeah, this is way better. Like so, Lambert doesn't have a roughness. Lambert doesn't have a roughness that affects the diffuse. This Ornaya function does. So if you look at the diffuse here, here's Lambert at 0 roughness, and after 0 we change to Ornaya, and that just looks way. It's got a nicer sort of like soft part with the light. Yeah, and then as you increase, yeah, it just changes a bit. Yeah, I think I like this one actually. Different though. Yeah, I'm not sure if it's correct though, because I just took it from the internet somewhere. But I can always just look at it later. But yeah, I want to try and use this one now. It just looks way nicer. Right, I might record that and put that in the devlog somewhere. Which means I've got to do it on the other maps as well. There's a Lambert. Where is the KD? Oh, I didn't multiply by the KD though. Yeah, you need to multiply that by the KD, man. I kind of did this a bit wrong, not gonna lie. Can we go back and look at that? Because it's not good. Right, Ornaya. Oh, I've already got that there. Good. Right, so Ornaya. Ornaya. Right, so actually it was a little bit wrong what I was looking at. So let's look at the actual final diffuse and see that again. Alright, now let's see this again in action. So roughness 0 is Lambert, Ornaya. Right, that looks even more different. Like the difference in lighting is it's a lot dimmer, but it looks much better. Like in my opinion. So here's just the diffuse. Get rid of that annoying second light. This is Lambert, Ornaya. Right, I just made it a bit dimmer. But yeah. Interesting, right? So let's now apply that everywhere else. We've not applied it everywhere else. Yeah, I want to keep this here. You know, let's do a little recording of that. Right, so actually I got a bit interested in looking at what different diffuse models there are. And there's actually this one called the Oren-Naya diffuse calculation, which is different from the Lambert one. Lambert is just albedo divided by pi. It's dead simple, but it's nice and quick, easy to compute. But it doesn't look as good as it can. So there's some more sort of physically based ones. So I got this implementation from the internet somewhere. This is one that I tried, and it just ended up looking quite nice. There are some other ones out there which were different, so I'm a bit on the edge if this one is correct. But in the future I'll look at it and more in depth. But I just thought I want to show how this actually looks and how it compares. So the thing that's different about it to Lambert as well is it also takes the roughness into account. And so it will change as the roughness increases or decreases. So the way I compare it side by side, if you will, is we just have this, that roughness slider that we've got. When it's 0, it just does Lambert. And for all the others, it does the Oren-Naya. So let's go and see how that looks now. Oren-Naya. Also, the name just sounds much better, doesn't it? Right. Okay, so this is us viewing the final fully shaded thing. Bearing in mind, I've not applied the Oren-Naya to any of the ambient irradiance map yet. That's something that's still got to come on. But you can already tell with the direct lighting. I'm just going to get rid of the blue light because it's kind of annoying. But you'll see here, as soon as we switch from Lambert here to Oren-Naya, it's already it just feels a lot softer and subtle, right? And as we increase the roughness, the diffuse changes a bit, I guess. But if you really want to see it, we've got to look at the debug view mode. So here's the direct lighting diffuse. So here's the Lambert. Here's the Oren-Naya. And as we increase it, it sort of gets a little bit brighter up here, right? So I'm just going to monkey around with that a bit. Right, so I'm just going to plug it now into the ambient light thing and just see it. We'll see what it looks like fully next. Oren-Naya radiance. Yeah. So let's get rid of this Lambert. Here's Lambert. Right, so irradiance. Render irradiance map. Bum, 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 bum. So where's the Lambert? Here. And multiplies it by pi. Bit of pi. Alright. I gotta get this right. So it does a multiply by the inverse of that, which basically is doing a division on pi. That divided by number of samples. Divided by number of samples. Pi divided by number of samples. Gotta get this right. So you can put the Oren-Naya in there. Bit of Oren-Naya. The problem. Let's get this right. There is a divide by pi in here. Gotta be super careful. So you accumulate the irradiance. Color. It just sums the irradiance. So if you do the Oren-Naya normal dot light. Can you do it in the irradiance then? Because you're shooting over the hemisphere, right? So let's slide that in it. So we've got pixel that we've got a normal to. And then you've got all the rays which shoot over the hemisphere. And so where's the light? Well, the normal's that way. The light is technically that way. Well, no, is it? The light is the sample direction. Is it? Yeah, normal. Where's the view direction? Yeah, you're gonna have to it probably won't be correct, but it's fine, it's just ambient anyway. But yeah, it'd be, yeah, it's just man, that looks way better. I can see it already from here. Like, that just looks way better. But yeah. So you're saying for this surface normal, you're sampling over there, which is, I guess, where the light is coming from. Yeah. So your view, where's is it light dot view? You'd have to do it per one of these. And that would be expensive. But it is on, so the view though, you might have to make the view and like one of the vectors the same. So your n dot l, so those are the same. I guess it's just squaring it. So I imagine if it's a viewing angle though. What do we do in the reflectance one? You know, the pre-filter. The reflect ray and the normal. It all just use the normal. And the light is calculated. Normal dot light, normal dot half vector, normal dot view. The view ended up being the normal in this one. So the light, yeah, will be the sample direction. So I think we'll have to do this per here. So you got the color, that'd be the albedo. Wait a minute. The albedo. That's the surface color. So you won't, this is irradiance. So you wouldn't do it in here. So you wouldn't do it in the irradiance map. You would do it. Maybe we can do the ambient. Let's have a gander. So ambient. So the divide by pi has already been done on the irradiance. Gotta be careful. So it's just divide by pi. So I think we need to remove that divide by pi. That's the only thing. Yeah, so render irradiance. But I think you have to remove that divide by pi. Do that still. So remove the divide by pi. And then in the calculate irradiance, we want to take the Orandaya. And then at the end, be correct. Yes, the average of everything coming in. And then, for crying out loud, we don't have the n.ls and all that. Wait, there's no light. You make the light the same as the view, isn't it? N.view, I guess. Right, so that one, so they'll be the same. Normal dot light? I guess they'll all just be the same. Yeah, this can't be right. Can't be right. It's probably got to be a bit of a different bit of maths. Yeah, it's probably got to be a bit of different maths, but that'll be then. That's the diffuse. Let's just see how it looks. I wonder if it's too bright or not. Right, I did ask a question. Omega C. Kinda, yeah. It seems like audience 3 is this time image at the top. Interesting. Take a gander at the. Has this tiny image on the top slide. NVIDIA's architecture, we can show off their block diagrams. Oh yeah, these block diagrams, sure. Yeah, so you got your scalar, your vector units. Alright. And then you got your... I thought they had scalar registers in NVIDIA these days. Because it can be a bit of a benefit, right? You can reduce the vector register pressure, isn't it? Let's get that block diagram, right? Right. Um. Hmm. Yeah, I'm not sure if I understand. So this is a L0 cache. This is probably a... Right, this is a... I get it now. This is like a compute unit. Alright, I wonder why there's 16 of these, 16 of those. And 8 of these. Oh. SM. What SM means nowadays. Made a small mistake at sending you the Lovelace block diagram. Here's the Ampere one, right? Ah, so they have half registers for in and right. Interesting. Tensor cores. Whoa. Yeah, I don't quite get what's going on exactly. Yeah, fair play. Think about some other time, I guess. Diffuse. Yeah, so let's see how this looks. I don't know if this is correct. This is me just fluking a bit of maths, not gonna lie, and it looks really weird. Does it? So let's look at that ambient. Is that a bit too bright? It's not really getting the color from that. Yeah, there's too many. The dot products are all kind of the same. So I think it's kind of looks like the opposite of the Fresnel, really. Yeah, those dot products. I think it needs to have a bit of the Oranier, like part of it. And you know what? There's that other link we got to that Material X thing. So they do like yeah, the Monte Carlo thing. That's reflectance though. Use it for reflect too. Right, you can also have the Orania for reflect as well. I realize. Yeah, this one was a bit wrong. Like this one, we didn't use that one in the end. It wasn't as good. So I think let's go back to here then. Maybe the Orania goes in here, then you take the average and then throw it out. Oh, for crying out loud. Yeah, so I think that's the radiance. It's the radiance coming in though. Yeah, I don't know how I would do it, to be honest. I don't really think I can do it. But anyway, it was an improvement. Just doing it alone for the direct line. Yeah. Yeah, I wonder how you do Orania for when you cache radiance. Yeah, then you look up the cache radiance and just apply it afterwards. Hmm. Yeah. Okay, that's cool. Right. So I'm gonna. Okay, so I guess let's quickly discuss like. So we've completed PBR now. I got a recorded devlog, which is coming out soon. Whenever I get that done, should come out maybe tomorrow if I get it edited during my lunchtime. If not, it'll be probably a bit on during the week. But so the next set of steps is to redo the renderer. I don't like the tile binned renderer anymore. So we're going to do a few things. We're going to refactor the code base. So we're going to have we've currently got our engine and the game all in one place. It is a game without an engine, but it's kind of nice having a separation between the engine layer and the game layer. To make that a little bit more explicit, so we're going to have an engine folder and move the core in there, GPU, operating system, UI, and then we'll have a GUI, which would be for the game itself, and the UI is just the UI library, if you will, that's built specifically for the game, and the GFX is the game graphics on top. Everything is kind of clean except for GFX because we've just been monkeying around and just getting the quickest thing in and to try out how things, well, I want things to be. I think I've found what I want things to be. So we're going to be copying and pasting this into an old graphics folder, and then we'll be starting from scratch, but it's not really from nothing. We'll just copy and paste all the stuff and make it all nice and clean. So I think I want to do that next stream. Just get this nice refactor in, and then we're going to be making a start on a BVH ray tracer, not using the ray tracing API. We'll just be doing it. We've already done a BVH ray tracer before. We've got code for that, so we'll just be redoing that in a better way, and this will allow us to do something. Yeah, it's gonna have a slight twist to it as well. It's gonna be got a kind of unique twist to the BVH, which we'll go into when we get into that. So that's the next set of things we're going to do, and then we'll go and do probably some editor or something, so we can actually build some scenes. But yeah, this is cool. I'm happy with how PBR's turned out. We'll see how we'll go from here. All right. So let me figure out who's on. You can either have full rate play 32 or half rate play 32 when you're using integer instructions. Oh, okay. Yeah, it's half rate ints. Wait, is it? No, int is always at half rate. If I'm understanding the diagram, you've only got one of these. Yeah, int is always at half rate. Wait. Half rate compared to the floating point, right? Because it's either you have ints or you don't. Yeah, the full rate of ints is the half. half as great as like them. Yeah, I see. But you want ints, right? That's kind of weird though. You have like one int, and then it's like, no, it probably doesn't work that way. It probably might just use a register, maybe. Or, yeah, probably one int doesn't make them all integers. That'd be weird. That's what I think, at least. Trade-off between AOE complexity and speed. Right. Fair play. Yeah, some really, really clever stuff that goes on in GPs these days. Hey, it's the Zig guy. You guys made the video editor. Let's raid him. The Zig guy. Right. Thank you for coming, everyone. I'll see you all on Tuesday, if not Thursday. Check out Twitch if you want to get the exact times. Similar sort of time to today. But yeah, I'll see you in a future one. Thank you for coming. Catch you later.